Hello,
Hi, sir.
just a second. Are you able to hear me now?
Yes, sir.
Okay, all right. So let us get started. Uh, so how should we take questions? Should we just directly start taking questions, or do we need to do any revision?
Sir,
Capacious, your voice.
uh, sir, I wanted to I was not clear how 2PC was working, a two-phase commit. So it would be helpful if you could revise that.
Okay, so we'll discuss
Yes, sir.
two-phase commit. What else?
Also, sir, can you just clarify, is fault tolerance, will questions related to fault tolerance will be a part of syllabus or not?
No, no. So we won't have questions related to fault tolerance theory, but we will have questions related to raft and things related to raft. So raft also has some fault tolerance in that, right?
Yeah, sure.
Uh,
Thank you.
so any other topic which you want me to discuss? Okay. So let me just.
Sir, I also want कि you please discuss the difficulty वाला part of blockchains.
Uh, what do you mean by that? So
Sir,
how?
I wanted I'm not understanding how the difficulty is increasing at the steps and how we are checking in between, like it is correct or not.
Okay, so we'll discuss like some topics related to blockchain also. So we'll discuss two-phase commit. We'll discuss the proof of work algorithm for blockchain. Anything else? Okay, so then let me first discuss two-phase commit. Then we'll take questions on two-phase commit. Just a second, I am just opening these slides for two-phase commit. All right, so these slides are also available on the Google Doc for the course material. So I'm using the same set of slides. So I'll skip, I think, the introduction part. This is very straightforward. So I'll directly come to the two-phase commit part. So yeah, just a bit of a background. Why do we even need two-phase commit? So in the class, we had discussed that let's say we want to build a web service where we have a web front end. So this is the server to which all the client requests are going to come. And then we have a database which is accessed by the server for retrieving, for reading any information or writing any information. Now, uh, we discussed how do we make this scalable and fault tolerant. So for scalability, what we said was that we will actually have more than one web servers, so multiple servers. So the client requests are partitioned across multiple servers. And then in the database layer also, we have multiple, the data is partitioned into multiple shards. right? And each, so we have multiple shards. So by shard, what we mean is, let's say we have in a database, let's say we have 10 million records. And let's say we have 10 shards of the database. And let's say each shard is having equal number of records. So each shard will have 1 million records. So there is no replication here. We are just partitioning the data into multiple shards, multiple partitions, so that we can query each of these shards in parallel based on, so different client requests can go to different shards, and this will make the system more scalable. So from the perspective of transactions, what is going to happen is, it is possible that a particular transaction has multiple operations, and it is possible that, let's say, it has 5 operations. Just an example. So it's possible that first operation goes to shard 1. So let's say operations 1, 2, and 3 go to 1, 2, and 4, let's say. Go to shard 1, and 3 and 5 go to shard 2. So transaction means that all the operations within the transaction, so either all the operations within the transaction should get executed and committed, or none of them should get executed and committed. So if all the operations were on the same shard, then we don't need any additional tool for ensuring that all the operations have committed. But since the operations are spanning across multiple shards, we need something called as two-phase commit. So here I'm just trying to motivate why do we need two-phase commit. So we need two-phase commit to coordinate between multiple shards to ensure that either all the shards commit their operations or none of them commit their operations with respect to a particular transaction. So in this case, shard 1 and shard 2 need to coordinate with each other to ensure that if shard 1 has committed operation 1, 2, 4, shard 2 should commit 3 and 5. If shard 2 has aborted or rejected or has not committed operation 3 and 5, or aborted operation 3 and 5, then shard 1 should also abort operation 1, 2, and 4, so as to ensure that all the operations in the transaction are aborted. So that was the underlying motivation for using two-phase commit. So this also discusses how do we achieve fault tolerance. We do this by a replication, and then replication is achieved via raft. So that is not part of two-phase commit, that we have discussed separately. So here it says what are the challenges due to sharding. So case 1, no transactions ever span multiple shards. So if this was the case, then we just use the machinery required to perform transactions on a single server database or a single shard database. Case 2 is transactions are spanning multiple shards, which I just explained. So in that case, what is going to happen is we have to ensure that shards participating on any transaction need to agree on whether or not to commit a particular transaction. Right, and these things are secondary. When to release the locks, they should release the locks only when all of them have committed the uh, operation, committed all the operations within a transaction. Okay, so then let us discuss two-phase commit. So in the two-phase commit, what happens is the setup. First of all, what is the setup? We have what we call as a TC. So TC is, I think, standing for transaction coordinator. And transaction coordinator is coordinating with each of these shards. So this is, let's say, shard A, shard B, and shard C. So for the sake of simplicity, let us just assume that the transaction coordinator is separate from all of these shards. But in general, what is possible is we have n shards, and we use a leader election algorithm to decide to elect the TC among the shards. Just like we have a primary server in case of primary backup protocol, or the leader in case of Raft. But here what we are, so for the sake of simplicity, let's just assume that transaction coordinator is separate from all of these shards, right? And transaction coordinator is coordinating between different shards. So feel free to interrupt me in between if you have any questions or if something is not clear.
Sir, does
Yeah.
the transaction coordinator also store data?
No. So data is stored by shard A, shard B, shard C.
Okay, sir.
Yeah. So transaction coordinator, as the name suggests, it is just coordinating between multiple shards.
So, but you said when there are n shards, there will be leader election among the shards. So one of
Right.
the
So
shard,
that is the general setting. So here, that is what I was saying. For the sake of simplicity, let us assume that the transaction coordinator is separate from these n shards.
okay,
But
but in general,
in general, it is possible that one of the shards becomes the transaction coordinator. So it acts as a coordinator between all of the shards, including itself.
okay, sir.
Okay. So whatever commands it is sending, whatever instructions it is sending to other shards, it will also send to itself. So it is not very different. This general case is not very different. The entire procedure will remain exactly the same. Just that it will also be sending the same instructions to itself also. Okay.
Yes, sir.
Okay. So two-phase commit, as the name suggests, it has two phases. One is the prepare phase. Second is the commit phase. So actually the protocol is very simple. So let me finish the protocol in 5 to 7 minutes, and then we'll take as many questions as required. Okay. So it has two phases. One is prepare phase. Second is commit phase. And in the prepare phase, what happens is the transaction coordinator. So it's also important to visualize, like, when are we committing. So let's go back. No, so let me just add a slide here just to explain I mean, make this more clear. I think this will help. So when you're writing your code, how will the code be written? So let's say you're writing a code for a distributed transaction on this distributed system. So your code will look like this. So you begin the transaction. So there would be a command which says begin transaction, right? And then you have op1, op2, op-n, and then you try to commit. Right? And then, so this would be in a try catch block, right? So you try to do this. If something fails, then you catch it in an exception block where you say abort. All right, something like this will happen. So this is your code which is going to run on top of this distributed system. Now it is possible that op1 is going to be executed on shard 1. This is going to be executed on shard 3. This is going to be executed on shard 5, and so on. Right? So different operations will get executed on different shards. And so this line here, this is what is, so this command here, commit transaction. So we are discussing whatever we are discussing about two-phase commit. It's just about this line. Like when we call this commit transaction command, what happens after that? And so this is implemented as a two-phase commit. Right? So so these operations have already been performed. So in the class there was a question, why do we even need two phases? So there were some questions related to there were some questions which will be answered when we understand that all the operations in the transaction have already been executed, just that they have not been committed in the database or in the shard. So these are already executed.
So, sir, begin transaction function here is not like starting two-phase commit.
Yes, exactly. That is what I want to emphasize. When we say, so two-phase commit has nothing to do with begin transaction. It has only to do with this commit transaction command. So
Okay.
this is an important clarification or understanding which we should have for understanding, for completely understanding two-phase commit. Otherwise, some of the things which two-phase commit is doing might appear redundant. Okay.
Yes, sir.
Okay. All right. So now let's go back to two-phase commit. And so what is happening is, so when the transaction coordinator receives this command of commit, what it does is it first checks whether all the shards are ready to commit or not. It first needs to know whether all the shards have executed their respective operations and they are ready to commit or not. That is why it sends this prepare command. So this prepare command is sent just to check shards are alive, they are ready to commit and so on, right? So if everything is working normally, everything is functioning normally, what will happen is transaction coordinator will send a prepare command. Each of these shards will respond with we are ready, prepare okay, right? So each of these commands, each of these shards return prepare okay. Now,
Yeah,
as soon
sir,
as the yeah,
sorry for interrupting, but this
sure.
prepare command is sent after the operations have been executed, so it has nothing to do with them uh, failing their operations.
Yes, yes. So no, no. So when I said already executed, so let me correct myself. So they are already yes. So they are executed in the sense that so you're right. So they are executed, or more generally, what we can say is they have already been communicated to the uh, individual shards.
Sir, can we relate this to a raft in which each and every uh, node has already written the operation uh, in its uh, in its individual node, but it is not already executed yet or committed yet.
No, no. So the exact implementation will vary from system to system. Uh, Generally speaking, uh, in general, what so when we are saying these operations have been executed, so what I'm trying to say is that they have been communicated to the individual shards. So it depends, right? Which of these operations depend on each other. So all of those things will come into picture, right? All of which of these operations. So for example, let's say there is this operation 5 here, right? So it is possible that operation 5 has no dependency on the first 4 operations. So in that case, some of these operations can be executed in parallel also, right? So there is no way for so there is no so if you want to make it more strict, then we can assume that all the operations are already executed by the time we come to commit. But it is possible that some of the shards are still processing some of these operations. So yeah, so let's keep it more general. So when we say that this commit command reaches the transaction coordinator, these operations have already been communicated to the individual shards. So it is possible that some of the shards, some ops fail, in which case, uh, the shard will return that it is not ready, it is not prepared to commit, or it will just send prepare fail command. So some ops may fail even if all ops have uh, successfully been executed. Then also there are other scenarios, right? When, for example, a shard has failed, right, due to some other reason, power failure or something like that, right?
Uh, so, sir, when we are saying that the operations are communicated to individuals, it basically means that the shard knows I need to perform this operation, or that did it
Yes,
already perform this operation.
yes. So let us consider a general scenario where these operations have already been communicated to the individual shards. Now it will now how what exactly do we mean by already communicated? So that will vary from system to system. as I just explained some examples, for example, it is possible that some of them could be synchronous operations, some of them could be asynchronous. Some of the operations might depend on the previous set of operations. Some of the operations may be independent. So based on that, it is possible to execute some of these operations in parallel or concurrently, right? So transaction coordinator, so to say, is sort of not keeping track of which operations have been executed, which operations are in pipeline and so on. It is just uh, uh, communicating all of these operations to the individual shards. So Mitakshi, is it clear?
Yes, sir.
Okay.
Excuse me, sir.
Yeah.
So in the prepare message, was the TC actually communicating these operations to shards?
No. So that is what I wanted to say. These have already been communicated. So when we say two-phase commit, and within this two-phase commit, prepare and commit phase. So these two phases, so all of it, whatever we are doing within this two-phase commit is part of this commit transaction command.
Okay.
All the operations have already been communicated. Some of them have succeeded, some of them are in progress, and so on. Okay. So ideally, so let's first discuss the algorithm. I think there can always be corner cases. So when we say prepare, when the transaction coordinator sends the prepare command, right? So then if everything is functioning normally, we assume that all the operations have already been executed, already been completed. So then each shard can say, I am ready for committing these operations. So it sends this prepare OK command. Once the transaction coordinator receives the prepare OK command from all, so note that it has to receive this prepare OK from all, not just from majority. So this is a big difference between Raft and two-phase commit, that Raft requires just a majority votes, but here it requires two-phase commit requires all votes, or all votes to be equal to prepare OK. So once the transaction coordinator has received prepare OK from all the shards, it will then go ahead and send this commit command. And once each shard receives this commit command, it will now go ahead and commit the operations into the database or into the storage, right? And due to some reason, let's say the commit failed due to XYZ reason, then so if the commit succeeds, then the shard will send OK to the transaction coordinator, and so transaction coordinator will now wait. It will now wait. So ideal case is that transaction coordinator receives OK from all, in which case it will conclude that the distributed transaction has committed successfully, and then it will move on to the next set of transactions. Okay, so that is the ideal case. Transaction coordinator sends this prepare command. Each shard sends the prepare OK response. Then the transaction coordinator sends this commit command. Each shard commits the transaction, commits its own set of operations in that transaction, sends back the OK response. Transaction coordinator receives the OK response from all the shards, and then it concludes that the transaction has committed successfully, right? So is the high level algorithm clear? Very simple, right? Just two phases and one request, one response. Transaction coordinator sends a request, waits for response from all the shards. Based on that, it decides whether to commit or abort, and then again waits for the response from the shards, and then based on that, it concludes whether the transaction has committed or successfully finished or not. Okay, so
Sir,
yeah,
I am still a little unclear in the distinction that we are saying that operations are already executed. So
right.
what is getting committed in the commit phase?
Right. So then we'll come to what Raghav was saying about can be related to this Raft. So we'll come to that. So I'll come back to your answer. So I think this answer is there in the slides. So this is what I was just trying to explain, right? When we say begin, client library begins a transaction on each separate shard, right? So here actually it is saying that client is directly sending the operations to the corresponding shard server. So that is also possible, right? If we don't go through the transaction coordinator, right? Say op1 goes to server 1, op2 goes to server 2, and so on. And then so I'll come back to your question, Hitesh. Just keep it with you. We'll come back to your question, right? So here, let's just take a look at some of these operations in a bit more detail, right? So this is what I was referring to. It is possible that the transaction coordinator, right? It is an independent entity. So in this case, the client is acting as the transaction coordinator, or it could be one of the shards which has become the transaction coordinator, right? So it is just showing the prepare phase. It sends the prepare command, and then so when this shard receives the prepare command, what does it do? So let's actually take a look. What does it do? While holding locks, whatever locks it needed for the transaction, can it commit the transaction? The answer is no, right? And so based on what condition the shard is in, what situation the shard is in, it will either send prepare okay or fail. And whatever command it sends, first of all, it writes to a log file. So each shard is actually keeping a log file similar to what we have in Raft, right? So whatever operations each shard is performing, it is first writing into the log file, and then only it is executing that operation. So in this case, let's say it is sending this prepare okay command to the transaction coordinator, right? So in this case, it will first write it to the log file. So this is called as write ahead logging, WAL. So we need not worry about what is write ahead logging. It is just a method of writing the operations onto the log file. So this prepare okay command is written to the log file, and then this command is sent to the transaction coordinator, and then it waits to hear response from the transaction coordinator. So Hitesh, coming back to your question, so let's take a step back. In operating system, what happens when you actually say file.write? So there is something called as buffer write. So you write your contents in the buffer, and only when the buffer gets flushed to the disk, then only we are sure that the data has been written onto the disk, or the file has been overwritten or created, and so on, right? So there is this notion of so even though we have executed this file.write, it is not ensured that the data has been flushed onto the disk, right? Similar scenario happens here also. When we say that operations have been communicated to the shard and the shard has executed these operations, so it is similar to, it has written to a log file and it has probably executed these operations and stored the results in a buffer. Now this buffer will be an in-memory block, and that needs to be flushed to the disk. Something like this happens when we say uncommitted operations and committed operations. So the difference is precisely, here we are talking about the operations have been written to the log file and or in the buffer, in memory buffer. Here we say that the operations have been committed to the disk or flushed to the disk. The results have been executed, committed to the disk. Does this answer your question, Hitesh?
Yes, sir.
Okay. So this is very similar to how we function in a single server file read and file write. Okay. So when the transaction coordinator, so notice that we're still in the prepare phase. So when the transaction coordinator receives the prepare okay or fail, right? So if it receives prepare okay, then it sends the commit command to all the shards. If it receives a prepare fail from even one of the shards, then it is going to send abort. The shards are not ready for committing, so it will just send abort the transaction, right? And before sending, it will write. So whatever operations a transaction coordinator is performing or a shard is performing, first that operation is written to a log file. This is again a log file. And once the operation is written to the log file, then the outcome and then the operation is sent to the participants. Okay, now let's go to the commit phase. In the commit phase, when the shard receives a commit message, right? So what will happen is, so if it receives commit, so in this case, you notice that once the transaction coordinator has decided that the transaction should be committed. Now the transaction coordinator has to ensure that each shard commits its operations, because each shard has previously sent a prepare OK response, then only it sent this commit message, commit command to all the shards, right? So in this case, the transaction coordinator may have to send this commit command again and again until the shard agrees and sends back the response that it has already committed the transaction. So once the transaction coordinator has concluded that the outcome of the transaction should be commit, there is no going back for any shard. So if a shard, let's say, fails, the transaction coordinator will keep on pinging the shard again and again, that shard again and again, until that shard comes up again and commits the transaction. So that is what it is saying here. Based on what command it receives from the transaction coordinator, either commit or abort, it will first write that in WAL, the write ahead log file. And if the command is abort, then it will revert all the transactions, all the operations within that transaction using the write ahead logging. So this you should have studied in database course. So even if you have not studied or if you have forgotten, that's fine. Just assume that when the shard receives abort command, there is some way for the shard has sufficient amount of information with it to revert back all the operations which it has executed. And then it releases all the locks, because transactions require acquiring of some locks. And then it sends an OK command to the transaction coordinator. So here, notice that it is written, TC will keep retrying to send outcome to the participants until it has OK from all. So it is the duty of the transaction coordinator to ensure that all the participants have either committed or aborted based on whatever the TC decided. Right, and then there are some scenarios here. So I'll take a pause here. So any questions so far on two-phase commit? So I've already explained the algorithm, but any questions?
Sir, does TC also write in logs that either you need to commit or abort the operation basically?
Just can you repeat your question?
Does TC also write in the log the operation it has decided for the shards?
Yes. So right here, right? So upon receipt of prepare OK or fail from all participants, right? Write outcome to WAL. So WAL is the log file. So first it writes the outcome which it has, which it is going to communicate to all the participants, and then it communicates the outcome to all the participants.
So,
yeah.
So what if one of the commit commands fails? Like what if
on the shard?
Yeah. What if the shard
Right.
does not
So
receive a commit command properly?
right. So in this case, this 4.4 happens. The TC will keep retrying to send outcome to each participant, whoever has not returned an OK.
Okay, sir.
Okay.
Sir, all the locks are acquired in the prepare phase, right?
No. So locks are acquired even before that. So we'll have to go back where we were. The locks are acquired depends on what kind of locking mechanism you are using. So locks are either acquired here, or definitely locks are acquired before the last operation. So commit transaction or the two-phase commit has nothing to do with locking. So there is this two-phase locking algorithm.
Right.
And then there is two-phase commit. So two-phase commit and two-phase locking, there is no relation between the two.
Well, then what's the purpose of prepare specifically? Because I from what I understand, prepare means that it's a promise to commit when asked, right?
Yes, it's a promise to commit.
Right. So if you are not acquiring locks even before the commit has not begun, like even before you are acquiring the lock. So I'm.
So let's go back to what I answered to Hitesh. Let's say you just forget the entire this distributed systems thing. Consider a single server where you are doing these file read, file write operations. Right? So let's say if you were doing some file dot write, right? And then you move on to the next operation, which says, let's say file dot read. Is it ensured that you will always get the latest content here in this file dot read once you have executed file dot read, right?
No.
Probably no, because it is possible that whatever you've written, it is still lying in the buffer and that has not been flushed yet. Right?
Right.
So commit specifically means that whatever you have written in the buffer, you want to push it to the disk. So it is sort of a flush. So commit is, you can say, loosely related to loosely referring to this flush thing here. Right? So now the question would be, so can you imagine that even if you've written some content to the buffer, it is possible that the flush fails?
Right.
Right? Because for example, let's say there is some condition which says if the file already exists, then you should throw an error. So it is possible that during the buffer write, so I'm not saying this is how exactly it works, and there are multiple possibilities. I'm just trying to motivate that there is a possibility, even if this file.write has finished, the actual file is not written to the disk and that fails. Right?
Yes.
Or more simply, let's say you have done file.write and you are on file.read, and now the machine stops all of a sudden, due to power failure. So it is possible that the flush command has not yet been executed. So it is possible that there are failures even after you've acquired all the logs and you've done all the processing and all that before the commit. Does this answer your question?
Yes.
Okay.
Sir, does the transaction coordinator keep on waiting? Like, is it a blocking call at the transaction coordinator when it keeps on waiting for okay from all the servers?
So as soon as the transaction coordinator decides the outcome, it has already sent the outcome to the client. So from the client's perspective, it is a non-blocking call. But from the transaction coordinator's perspective, it will still wait for all the participants to send back the the OK message that it has successfully registered and executed the outcome.
So what if like one of the client sends instead of okay it said fails? So will the transaction coordinator then send a global abort to all the servers?
No, so transaction coordinator has already sent the outcome to the shards, right, to the participants. So now it is not going to change its outcome. So once the transaction coordinator decided whether to commit or abort, it is not going to go back.
Okay, so like if the let's say S1 sends a fail message in the fourth step, so transaction coordinator will retry commit on S1 till it sends a message.
Yes. So that is one of the limitations of two-phase commit, that it is possible that it is stuck forever.
Okay.
Sir, can S1 even send a fail message in step 4 or it can only send OK?
It can send a fail, right? So
Are there no timeouts, sir?
there are timeouts. So timeouts are handled similarly, right? So for example, let's say in prepare phase, there is a timeout. Transaction coordinator sent the prepare message and one of the shards was not able to respond within the timeout. Right? So in that case also it will send the abort message.
Okay.
Right? And similarly in the step 2 also, if the transaction coordinator sent a commit command to each of the shards and one of the shards is timed out, then it will resend the commit command. Does that make sense?
Yes, sir.
Okay.
And if the shards don't hear back from the coordinator, then?
Right. So that we'll discuss. So I think there are some scenarios wherein so we had, I think, similar questions in the quiz also. So that we'll discuss. So anything apart from like what happens if the shards don't hear from the transaction coordinator? So till now, I think all of the questions were centered around what if a particular shard fails, times out, and so on. So I think we have covered all of that. Now let's go to the more interesting part or more confusing part, where what happens if the shards don't listen from the transaction coordinator. So any other questions till now? Hitesh, is it clear? Okay, so let's see what all scenarios are here. So So I'll just scroll through what all scenarios are there in the slides, and if there are any more questions, we can discuss. So here what it says is S1, so transaction coordinator has sent a prepare command to all the shards, but S1 actually timed out. It did not receive the prepare from the transaction coordinator. So what it will do? So if S1 did not receive a prepare command in time from the transaction coordinator, then it will just go ahead and abort. Right. So so this abortion is safe, because once S1 aborts, then whenever the transaction coordinator resends this prepare command, it will just receive this prepare fail message, right? And then the transaction coordinator will send the abort message to everyone. Okay. Or the other possibility is that the prepare. So the possibility is this, right? So we had this. If there is a timeout from even one of the participants, then the outcome would be abort. So here what we're trying to discuss is TC sent the prepare command to all of the shards. S1 did not receive, but from TC's perspective, TC has already sent the prepare command and S1 has timed out. It has not sent a response back, right? So in this case, S1 will abort, and then TC will also abort because it has not received a response from one of the shards. Okay, so this is, I think, simple. So this is what. So I guess this slides are discussing these two cases separately. So one is the prepare command is not just received at the shard, right? And the second scenario is the prepare is received, but the prepare OK message is not received at the transaction coordinator. So in either case, the transaction will be aborted. So so once the transaction coordinator receives the prepare OK, once the transaction coordinator has not received, or TC times out waiting for the prepare OK fail from S1, then the transaction coordinator will just send the abort command to all the shards. Right. So this was an interesting scenario which we discussed in the
Sir, does
class.
abort release the locks also?
Yeah. So abort will release the locks. So when you abort, you release the locks also. Okay. All right. So if there is a timeout, so summary is, if there is a timeout in the prepare phase on either the transaction coordinator side or on the shard, any of the shard side, the transaction is going to be aborted safely by all the shards. Right. And the second part is during the commit phase, if there is a timeout. So for example, let's say S1 times out waiting for outcome from TC. So S1 has already sent prepare OK. No, so it depends what S1 has sent. So S1 has already responded back to the prepare command. It was either prepare OK, it was either prepare fail. So what should this S1 do while timing out for the outcome from the TC, right? So here are two cases. One is S1 had sent prepare OK. Second is S1 had sent prepare fail. Right? So for prepare fail, we discussed in the class that if S1 has sent prepare fail, then it is sure that the transaction will be aborted, because TC cannot proceed with commit even if one of the shards have responded with prepare fail. So in this case, it can safely abort. But in this case, it needs to know what the other shards had sent. So if all the other shards had sent prepare OK, then it should commit. And if any one of the shards had sent prepare fail, then it should abort. So in this case, it is actually stuck. If S1 is not able to receive the outcome from the transaction coordinator and it had sent prepare OK in the beginning, then it is actually stuck. It doesn't know what to do. It is not sure what it should do, because commit or abort depends on the response sent by the other shards in the prepare phase. Does this make sense? So these slides are just talking about this case. Case 1, S1 had sent prepare fail in prepare phase. So the action is say S1 can safely abort because it has sent prepare fail. So the transaction coordinator has to send abort to all the shards. And the second case is S1 had sent prepare OK, right? So in this case, it's not sure what it should do. Either it should commit or abort. So in this case, it runs a termination protocol. So we'll see what is the termination protocol. But until now, is this clear? Like what choices does S1 have if it has sent prepare fail or prepare OK? Okay. So what happens in a termination protocol? S1 will wait for the TC to come back, right? So recall that SI, the shard is still holding locks. Other possibility is it could ask other participants. It could ping other participants whether they received the outcome, and based on that, it can either commit or abort. If none of them received the outcome, that for example, let's say the TC died, right, or got network partition right before it sent the outcome, then participants are surely blocked till the transaction coordinator comes back. Or the other possibility is that I think other possibility could be someone else becomes the leader, right, and then tries to do the entire thing again. So does this make sense? Termination protocol. Okay.
Sir, so in this case, if one date they can all terminate, so we are checking that one shard or any shard got the response of commit or abort from the TC.
Yes. So if at least one of the participants, so here what this shard which did not receive the commit or abort message, what it is going to do is it is going to ping other participants. So I think so there are multiple implementations possible. You can ping them one by one, and until you receive a response, until someone responds back that I have already heard back from the transaction coordinator, and the transaction coordinator told me to commit or abort, and based on that, the other shards will also act accordingly. So the termination could be either commit or abort. It could be either of it. Okay.
Yes, sir.
Okay. So yeah, these are. So we were discussing about timeouts, but failures also similar analysis applied. I think we discussed some of these cases already. So some of the cases which are listed here is if participant is not in uncertainty period on recovery can decide what to do. So this you already discussed, right? It can, if it has sent prepare fail, then it can unilaterally abort if no decision, right? Otherwise do whatever the decision is. So I think so otherwise it has received the response from the TC, and in that case it will just act accordingly. And if the participant is in uncertainty period, it cannot decide on its own, so it should invoke the termination protocol. So notice that here the only additional thing is we are writing everything in the log file, right? So using the log file, the participant can check its current status. So whenever the participant comes back again after failing, after crashing, it will read the log file, check what was the latest entry in the log file. Based on that, it will decide how to proceed. So there was a question if 2PC is blocking or non-blocking. So it is blocking in a certain context. So it is blocking because a process can block indefinitely in its uncertainty period until a TC or a network failure is resolved. Right, and if TC is also a participant, then a single site failure can cause 2PC to block independently. And the block, and whenever the shard gets blocked, the locks are still being held, and therefore other transactions, right? They can't interact. They can't make progress. That is why we call 2PC as a blocking protocol. Okay, so it says 2PC is expensive because there are three. So the latency is computed in terms of these three message latencies. First, the coordinator has to send prepare, then wait for then the client, then the shards have to send prepare, okay, fail, and then the coordinator has to send abort commit. So it takes three messages to complete the commit, right? And then if there are n participants, then you will have 3 n messages. And then there are some optimizations, 3-phase commit, which resolve some of these problems, don't resolve all of them. So that is not part of the syllabus. So any questions on 2-phase commit? Okay, so I'm assuming that all of you have understood the 2-phase commit very well. So no questions on 2-phase commit? Okay, so then we can move forward. So anything else you want to discuss? So there were some questions. Yeah.
Sir, can you please specify the topics that are important for theory and those that are important for numericals or practical questions?
So as of now, my plan is that STFS and MapReduce, there will only be questions, the numerical questions, no theory.
Yes, sir.
Right? And Raft, it would be a mix of numericals and theory. So I think in Raft, if you understand the theory, you can answer the numericals also. So it's important you understand the theory of Raft. So theory is not in terms of like define, explain the entire process of leader election. So I'm not going to ask these questions. I'm going to ask specific questions. What happens in a particular scenario? What happens in X scenario, Y scenario, Z scenario, and so on.
Yes.
And so it doesn't require, I don't feel you need to mug up the entire algorithm as such. If you understand the algorithm, you should be able to answer the questions. Okay. So for 2-phase commit also, I think if you understand the algorithm, you should be able to answer the question. So 2-phase commit also, I don't see having any numerical questions, only conceptual reasoning questions. Yeah.
So in theory, there won't be question like advantages बताने हैं, disadvantages बताने हैं. Not exactly, but point to point. These.
See, I feel, I may be wrong, but I feel I never cut marks if you've not specified a particular term. If you have explained the answer, answered the question in your own language, as long as it is reasonable, I've always awarded marks, right? So when I say the questions would be theoretical, conceptual, logical, reasoning based, you might be asked like mention one advantage over this and this, mention one advantage of X over Y or Y over Z or whatever. But again, you don't need to mug up these advantages. If you understand the algorithm and if you have some idea of these algorithms, you should be able to answer. So I can't say like, I won't ask any questions such as what are the advantages of X and Y. So I may ask, all I'm trying to say is that, so when I said for SDFS and MapReduce, I'm telling upfront, I'm not asking these questions. What are the advantages of replication? Or what are how does MapReduce parallelize and all that? So I'm not asking those questions. I'm just asking numerical questions based on whatever we have discussed. So questions which are similar to the questions listed in the practice sheet for SDFS MapReduce. For Raft, I'm saying the questions will be a mix of theory and numericals. But if you understand the theory, you will be able to solve the numerical also. It's no big deal. For 2-phase commit also, there would be only theory. So by theory, I don't mean to I won't ask you explain the entire 2-phase commit, list each and every step which is involved in 2-phase commit. So I won't ask such questions. I will ask questions related to specific scenarios which might arise in Raft, 2-phase commit and all that. So for this, you need to understand the algorithm. So what I'm trying to say is for Raft and 2-phase commit, make sure you understand the algorithm, right? And then based on that, you will be able to answer.
Okay, sir.
Okay.
Sir, what about Laporte distributed snapshot?
Right. So for distributed snapshots, we had discussed 2-3 examples in the class, right? So for distributed snapshots, there would be questions. So actually, I have not prepared the question paper yet. I am halfway through, right? So for distributed snapshots, I'm planning some questions based on the examples which we discussed in the class, and maybe some theoretical questions also.
Okay.
Okay. And then what is remaining? What BitTorrent and
Blockchain.
blockchain? So yeah,
Blockchain.
so only theoretical questions because we haven't done any numericals on them. Again, so I won't ask you to explain the entire blockchain, each and every step and all that. Maybe some portion of some part of the blockchain. Similarly in BitTorrent also.
So what's the duration of the exam?
2 hours. So this time I'm planning that. So my teaching philosophy is that I don't uh, uh, evaluate students on how fast they can write the exam. So that is why you must have noticed I always give as much time as you need for solving the question paper. So this time I'm planning to keep every time I plan, but I don't end up doing it. So this time I'm planning, I'll keep the question paper short so that you can definitely finish it in 2 hours. But I may not succeed also. So in that case, I'll give extra time.
Sir, can you please explain to question 5 in the practice question of 2PC?
Okay. Question 5. So let me share my screen. Oh, so screen is already shared, right?
सर एक चीज और
हाँ.
ब्लॉकचेन वाले में सर वो कोड वगैरह भी थे तो उस पे तो नहीं आएंगे
So
ना सर?
actually, can you? I mean, I also like interacting in Hindi, but there are some international students here, so you can speak in English.
Sorry, yeah. So in the blockchain slides, there were some codes for checking the codes and all and hash function and all. So do we need to go through them there as well, or just the theoretical aspects of the blockchain?
No, no. So I don't. I mean, I don't plan to ask any coding questions in the exam
Okay, great. Thank you.
because it's very difficult to evaluate them. Okay, so what was the question? Question 5, right? What happens if a node that has already committed the transaction fails before it can acknowledge the commit message from the coordinator in the two-phase commit protocol?
Here I have a doubt. What does it mean by already committing before the commit message from coordinator? Like, what is the meaning of node already committing before it has got the commit message from?
So see how it works is the following, right? So TC sends first the prepare message, then it receives the prepare OK from this node, and then the TC sends the commit message, right? Once the node receives the commit message, it is going to go ahead and commit the operations, right? It has to do some operations on its own end, right? On its end to commit the transaction. Is this clear? Like, I mean, it has to first perform some operations, then only it can send back that it has been successful in committing the transaction. So here I think what it is saying is it has done this part where it actually went ahead and committed the transaction, but it did not send back the OK command or the acknowledgement to the coordinator. Right. So let's see what is the response here. What it says. So coordinator will not receive an acknowledgement from that node. So coordinator will keep retrying to contact the failed node until the node comes live again and acknowledges back the request for committing the transaction. So does this make sense? So what I'm trying to say is that when the node receives the commit request from the coordinator, it will then go ahead and do something. And what is this something? It will commit the actual operations, and then it will send this OK message to the coordinator that it has successfully committed the operations. Samyak, does that? Yeah.
Yeah, yeah.
Uh, so if the transaction coordinator times out, then
Yes, the transaction coordinator will then keep
so,
retrying
like forever.
forever. Yes, that is why we just discussed it. It is a blocking protocol.
Okay. There's no timeout or as or something.
So this is basically there is no timeout, right? So you need to run a uh, yes.
So,
So yeah.
so
So just a
somewhere
second.
it's
Just a
written.
second. So there is no timeout, right? So that is the limitation of two-phase commit. That uh, once it has, I mean, the only possibility then is, let's say, if you think that the system is now in a corrupted state in which some shards have committed the transactions, other shards are not responding, so your system is in a corrupt state, inconsistent state. So in this case, what is feasible is you go back to a previous checkpoint and then start again from there. So that is still one solution. So it's a sort of a deadlock situation. You can think of it, how would you resolve deadlocks, right? So in deadlock also, you can't proceed forward until you restart the system and proceed, start from a previous checkpoint. Does this make sense?
Yes, sir, got it.
Yeah. Yes, Shelly.
Sir, somewhere it was written that if it times out, it will abort it will abort it and sends an abort message everywhere.
So let's see where it was written.
This or the video you shared, YouTube video, not sure.
No, I think what you might be referring is, so Shelly, there are multiple components here. So who times out and in what phase it times out, it depends on that. So are you referring to the specific question which we are discussing here, question number 5?
Yeah, like if a node times out, then like
If a node times out in what stage, what phase?
like when it is waiting for an acknowledgement. Though I'm not sure, but like yeah, I'm also not sure.
So I think there are like two phases, prepare phase and commit phase, and within that also we have two components, transaction coordinator and the shard or the individual node. So who times out and in what phase it times out, the answer will depend on that. Okay.
Okay, sir.
Sir, can we discuss the raft last question?
Raft last question. So this is an important question in the sense that if you understand this, then you probably understand all of Raft, or at least the leader election part.
Yes.
So
Yeah.
go on.
So my doubt here was when a network partition happens.
Hmm.
So let's say there are 7 nodes. So the majority will be 4, right?
Right.
So is this majority, this number is same across both the partitions, or it adjusts based on the partition number?
Based on the partition number, right? So actually, we discussed this in the last class, right? So let me discuss it again because it basically clarifies all of the concepts related to leader election. So uh, let me open a new slide. Okay, so network partition in Raft. Okay, so let's take Shaunak's scenario where he said that we have 7 nodes. So we have 7 nodes, 1, 2, 3, 4, 5, 6, 7. Okay, and let's say this is the leader right now, and term is equal to 1, which everyone is having term is equal to 1. So what do you want, Shaunak? Now, how should we proceed?
Split of 4:3.
4:3, right? So let's split. So let's say we have a network partition. Okay. So then what will happen? right?
Yep.
So 4:3, in 4:3 also there are two scenarios. The leader is in 4-node partition and the leader is in 3-node partition. So we can discuss both. So let's first
go with 4.
let's go with 4. Okay. So let's see. So let's have this partition. Okay. So the leader is in 4-node partition. Is that correct?
Yes, sir.
So in this case, what will happen is, what is the majority here? So raft requires majority votes from majority nodes to proceed forward, right? For append, so in raft there are only two RPCs, two types of operations: request vote, which are done in leader election, and append RPC, append entries RPC, which is fired by the leader for appending new request, new client request in the log file, new entries in the log file, right? So for making progress, the append entries, whenever a leader sends an append entries request to all the followers, it should receive a response back from a majority of the nodes. So what is this majority? So let's say if the n is equal to 7, majority, what would be majority? Majority would be 4. Now, an important point to note here is that this 4 is including the leader. So the leader has to wait for response only from 3 of the followers in this specific scenario. So in this case, since the leader still has access to these 3 followers, it will keep on making progress. These 3 nodes along with this leader will keep on making progress, right? And there will be no term change. In this partition, what will happen? Now these nodes are not able to contact the leader, existing leader. So what they will do, they will time out, right? So that is called as this heartbeat timeout. Right? Heartbeat timeout. Now, so they will start a new election. So when they start a new election, the term will change to t equal to 2. Right? So for the sake of simplicity, let us assume that only one of the nodes times out. So let's say this node times out. So it starts an election. Right? And then it will send this request vote RPC to these nodes. It will try to send to other nodes also, but it will not go. The request will not go through because of the network partition. So then let's say if it receives the request, the acceptance, vote acceptance from these 2 nodes, then also it doesn't have a majority because minimum number of votes required are 3 other than its own vote. Right? So minimum number of votes required are 3 for getting majority. So in this case, the term will keep on increasing and there would not be any leader. So these 3 nodes will not be able to make progress. Is this clear?
They are just not using.
Doesn't it already have 3 votes because it has 1 vote of its own in the 2 votes?
No, that is what I'm saying. Minimum number of votes other than itself.
Other than itself. Okay, right. So that is okay. So 4 votes are required. It doesn't.
Yeah, basically it's very simple, right? So the simple principle here is majority. For 7, what do we mean by majority? 4, right? 4 is the clear majority. Minimum number of nodes which form a majority is 4. Now you include that node itself, so you only need votes from 3 other nodes, right?
Yeah.
Let's say you are going into an election. Let's say there is a city in which only there are 7 citizens, and you want a majority, and you are also casting a vote. So your vote also be counted, right? And you will obviously vote for yourself. I mean, if you are electing the elections, if you are standing for the elections. So the same philosophy works here. So you cast a vote for yourself. So you add your own vote always. Okay.
Sir, can you please explain a distinction between election and heartbeat timeout? Like here, will the 3 nodes wait for the heartbeat timeout period or the election timeout period?
Yeah, so it's a good question. So this requires, you should be clear with this, that so the heartbeat timeout is associated with append entries request. So if a follower node doesn't receive an append entries request for the time duration equal to this heartbeat timeout, then it times out. And then it understands that it doesn't have access to the leader. So either the leader has died or it is not able to contact the leader. Right? The election timeout is related to this request vote RPC. So election timeout comes into play when an election is being held or when an election is being contested. Heartbeat timeout comes into play in ordinary situations where the election is already being held, leader is already elected, and the followers are just waiting for append entries RPC to make updates to their log files. Right. So election timeout, how does election timeout come into picture? If this node, let's say, has started the election, it will wait for this amount of time to receive all the majority votes. If it doesn't receive the majority votes, it increases its term and then restarts a new election. Does that make sense?
Yeah. So like, what is the then purpose of making election timeout as randomized and not the heartbeat time?
Yes. So, right. So what happens is, so if you don't keep, so in this case, what is happening is, so you keep both heartbeat timeout and election. So both heartbeat timeout and election timeout are random, right? And so this is also random. So election timeout is also random because it is possible that, so in the first scenario, yes. So for example, as in the first go, yes, you don't need the election timeout to be random. In the first iteration, when the heartbeat is missed for the first time, right? So in this case, since the heartbeat timeout is random, only one of these nodes will time out, right? And then it will start the election, right? But it is also possible that multiple nodes participate in the multiple. So eventually what will happen is all the nodes will time out on the heartbeat, right? And then they will start contesting the elections, right? So in a general setting, there could be a possibility that more than two nodes are conducting elections or are becoming candidates at the same time. So to reduce the probability of these multiple candidates standing for election at the same time, we have election timeout also as random. Okay.
Sir, I had a question. Let's say at t term equal to 3, the left side network partition heals. So would the node with t equal to 3 able to receive append entries from the leader because its
Can
term
you repeat your question?
So let's say at term equal to 3, the network partition heals.
Right.
So now would this node with term equal to 3 be able to receive appendment entry messages from the leader since its leader's term is t equal to 1?
It's a good question. So let me just check. No, so in this case, what will happen is, so my understanding is that, so someone can correct me if I'm wrong. Since these nodes have already increased their terms, right? What will happen is, so these nodes will be again and again conducting the elections, right? So I think they will reject the append entries message, and in response, they will also send their term number. Now this leader will now understand that there are some nodes which are on a higher term. So it will also give up its leadership and a new election will be held, right? And then in that case, again, whichever node has the most number of entries, that node will be elected as the leader, and then the system can start functioning normally as before.
So what will be the final term then at the end?
Depends on which. So because these three. So when the network partition heals, right? So T equal to 3. So whoever was at T equal to 3, none of them will actually win the election, right? And if because in the first iteration after the network partition has healed, only candidates would be one of these three, right? So they can't win the election because they don't have sufficient number of votes, and these nodes will not give votes to these three nodes because they don't have the sufficient number of entries. So I think what will eventually happen is they will all time out, and then someone from here has to contest the election. So at least the term would be T equal to 4.
But then it would not it be like the time is not increasing monotonically?
Term is increasing monotonously, right? Where it is not increasing monotonically.
Okay, so it doesn't mean it needs to increase by 1. It can increase by.
Yeah.
Okay.
So monotonically increasing means that it is increasing, right? It is never decreasing.
Sir.
Yeah.
Sir, to compare the logs of different nodes, I guess a tuple of the term and the length of the logs is used, right?
Right.
So when the partition is healed, I guess the first criteria is to compare the term itself.
Yes, that's what I'm saying. Yeah.
Right. So once the partition has gone,
Uh-huh.
the leader of the smaller, like the 3 nodes cluster, will have a higher term, right?
There is no leader in the 3-node cluster.
Oh, right. Sorry, I forgot. Yes.
Yeah.
No, but all three of these will have a higher term, right?
Yes.
So when there is another leader election uh, that will be taking place when the network partition heals. So in that tuple, these other nodes that were in the 4-node group would see that, oh, these nodes have higher term than us.
So what will happen is, so let me clarify. Uh, what should happen is, I mean, there's a 1% chance I might be wrong. So if I don't make sense, let me know. So what will happen is, let's say the network partition has healed and these three terms at equal to 3, right? So I've already written there. And these are all at T equal to 1. Now a request vote RPC will be sent. So let's say there is only one candidate. It will send the request vote RPC to all of these. Oh no, wait. So request vote RPCs will keep functioning like that. The other thing is append this leader. This leader will continue sending append entries RPC. So this will send append entry RPC to each of these nodes, right? And each of these nodes will reject the append entries RPC because their term is higher than the leader's term, right? Correct. When they reject, they will also inform that their term number. So when they reject, as response to this rejection, they will also inform the leader that they are on a higher term number. From this rejection, the leader will come to know. This leader will come to know that there is some of the nodes have advanced to T equal to 3. So this leader will now increase its term and give up its leadership. Wait for some leader to be elected. But in this case, in this T equal to 3, no leader can be elected because only candidate is this, and this cannot be made the leader because the other condition of its log being the most up to date is not satisfied. So none of these nodes will give a vote to this leader. So there are two things happening simultaneously. One is this request vote, other is append entries RPC. When the network partition heals, these two requests are being sent simultaneously. I mean, they are being sent at the same time, right? So when the append entry is rejected, the leader comes to know that its request cannot be accepted because it is at a lower term. So it will update its term, wait for a new leader to be elected. But in this T equal to 3, no leader can be elected because this candidate cannot be elected as the leader. It is not having the most up to date log. So in the next case, what will happen is eventually some of these will start contesting election and one of this will become the leader. So it could be in T equal to 4, T equal to 5 or any other further term.
Okay, sir, got it. So when the term eventually increases and becomes more than uh, all of these previous terms, that's when the
Yes.
leader will be elected. Got it.
So I had two questions. So So once a node sees in any request or response that the term is higher than its own term, it immediately overrides its own term number, right?
Correct.
Okay, and suppose what happens when, let's say, we are in a scenario that all of the nodes finally converge to the same term number, right? And
Right.
then again, one of the nodes times out and increases its own term.
Huh.
So again, this process, I guess, keeps continuing.
Yes.
So, sir, how when the three nodes which were cut off from the network previously, when come in sync with the rest of the network, the entries that were appended?
Right. So this much is clear. A new leader will be elected. So it will be, let's say, for the sake of simplicity, a new leader is elected at t equal to 4, and the leader could be one of these 4.
Yes, sir.
Right. So let's say this is the new leader now. Okay. Now, since this is the new leader, it will send these append entries message to all. So the sync of log. So whichever node has lagged behind, it will sync up its log with the leader using this append entries message. So append entries message will be sent to all the nodes, and the nodes will respond back. Whatever entries they are missing, those entries will be sent back by this leader.
Okay, sir.
So the syncing of logs happens via this append entries message.
Okay. Yes, sir.
So, I mean, frankly speaking, if you really want to understand draft, I would highly recommend you go through the paper. I mean, not for the sake of this exam, maybe for the sake of exam, you don't need to go through the paper. But if you really want to understand the draft algorithm in detail fully, it is worthwhile going through its original paper. It is, I think, 8 to 10 pages of theory, but it's a good article. So that should hopefully make all the doubts, concepts clear.
Sir, also according to you, there are two timeouts. One is the heartbeat timeout and one is the election timeout.
Yes.
So from what I knew, I think there was only one timeout. Heartbeat was the message things that were being sent. Okay, I will check.
No. So see, logically also, let's say, so there are two timeouts. I am sure. Let me just confirm again. Because let's say if everything is functioning normally, right? If everything is functioning normally, then there is no question of election timeout.
No, what I'm saying is the definition you have given for heartbeat timeout is the same for election timeout, and there is no that like election timeout waste for the request vote RPCs. I don't think there is a
So
timeout
let me
for
just
that.
confirm. So let me just refer to the paper. Let me just double check in the paper. So let me share the paper draft. I think what Shaunak is saying is right. So let's read this together. What it says. Raft uses a heartbeat mechanism to trigger leader election. When a server starts up, they begin as followers. A server remains in follower state as long as it receives valid RPCs from a leader or candidate. Leaders send periodic heartbeats, which are nothing but append entries RPCs, to all the followers in order to maintain their authority. If a follower receives no communication over a period of time, called the election timeout, then it assumes that there is no viable leader and begins an election to choose a new leader. So I think what Shaunak is saying is right. So there is nothing called as, so we'll just read this entire thing just to ensure we're not wrong again. So whenever a follower receives no communication over a period of time, and that period of time is essentially the election timeout, and then it will start a new election, right? And so to begin it, so then it explains how does an election work, right? So let's skip this. So let's read this. Draft uses randomized election timeouts to ensure that split votes are rare and that they are resolved quickly. To prevent split votes in the first place, election timeouts are chosen randomly from a fixed interval. This spreads out the servers so that in most cases, only a single server will timeout. It wins the election and sends heartbeats before any other servers timeout. The same mechanism is used to handle split votes. Each candidate restarts its randomized election timeout at the start of an election and it waits for that timeout to elapse before starting the next election. Right? This reduces the likelihood of another split vote in the new election. So I think, yeah, what Shaunak is saying is right. So I was wrong. So there are no two timeouts. There is only one timeout. And so the same timeout value is being used for waiting for the heartbeats or waiting to start a new election. If it doesn't receive a ping from the leader within that time, or if it doesn't win the election during that time. So is this clear? Let me clarify. So let me know if there is any doubt regarding this. So I think Samyak was asking, right? What is the use of election timeout being random when heartbeat timeout is already random? So my response, so answer which I gave was wrong because I mean I gave the right answer, but in the sense that these two are essentially the same.
Yeah, yes,
right. So the only thing which we need to change in our understanding is that both heartbeat timeout and election timeout are essentially referring to the same timeout. Okay, so any confusion regarding election timeout? So there is nothing called as heartbeat timeout. So let's just scrap this. Election timeout is being used for election timeout is used for waiting for the heartbeat. So if a follower doesn't receive the heartbeat within this election timeout period, then it starts a new election. And once it has started a new election, it will not restart the election until this election timeout has finished. Okay, so these are the two use cases of election timeout. So Shaunak, does this make sense?
Yes, sir.
Okay. So any other questions?
Sir, I have question, but it's regarding snapshot algorithm.
Yeah, so we'll come to snapshot algorithm. Let's finish draft first.
Okay.
Sir, another question I had.
Yeah.
Sir, when we are sending this append entries message, not as a normal log update, but only as a heartbeat, does there need to be any response from the nodes it has been sent to?
Can you repeat your question once?
So this append entries RPC, right? So it is doing the function of as a heartbeat also and as a log update also.
Yes.
So when we are sending it as a heartbeat to the normal nodes, does there need to be any response for the nodes to recognize the leader? Because I mean, because since the leader is just saying that I am the leader.
So what you're saying, when the append entries RPC is sending a heartbeat to the followers, when the leader is sending the heartbeat append entries RPC to the followers, so the followers need to respond back?
Yes.
So I think they need to respond back, right? Let me just double check.
Because once, okay, maybe.
I mean, if you. So let's say if you don't respond back.
No, what I was thinking was that since it has already voted for one leader, let's say, why would it need to respond again? But I guess there can be cases.
Right. So I think append entries is independent of the leader election, right? So append entries, the only role of append entries in leader election is that as soon as a follower or a candidate receives an append entry request from an existing leader, it will probably accept that leader as the leader.
Yeah. So, sir, actually, I was thinking on the basis of the first question you have given in the sheet.
What is the question?
Yeah, the first question. So I was wondering the last one, the response to the append entries, whether it was strictly necessary or not.
So I think it is required. So I mean, append entries in general requires a response. So I would guess even the heartbeat also requires a response. So it's because it's essentially the same RPC. It's the same RPC, just the contents of the RPC are different.
Right.
Yeah. So I think it would require it will require a response from the follower.
Okay.
Okay. So this figure 2 in the paper actually has a lot of information. Some of this we have not discussed, but I think a good amount of information we have discussed. So this sort of lays down all the rules by which the raft algorithm is governed, or the nodes in the raft cluster are governed. So you can take a look at some of these rules. So for example, what happens in append entries RPC, what are the arguments, what are the results? For example, request vote RPC, what does the receiver do, right? Receiver implementation. The receiver implementation. So let's actually just take a look at this to answer Shaunak's question more concretely. So the receiver which is receiving the append entries RPC, it will reply false if term is less than current term. It will reply false if log doesn't contain an entry at if the log if it doesn't have the entry which is required by the append entries RPC. So you may ignore this if because we have not discussed this very specifically in the class. And if an existing entry conflicts with a new one, delete the existing entry and all that it follows. So some of the details are missing here, but here it should give some idea. Right, so here I think it is not saying anywhere that it will not respond back. Right, so it should respond back. Okay.
Yes.
So any other questions on raft?
Also, sir, in the fifth question, you have asked like how does the raft algorithm ensure safety?
Right.
So can one of be the like I think another extra point can be that like at a single term only one single node can only give one vote.
A single
node can only give one vote.
Right. So here you need to write the important. So I think that could be part of the safety.
Yes.
Right.
Specifically for safety, I mean.
So actually, this question is directly taken from the paper. So paper has a separate section on safety.
Oh, okay.
Right. So if you want, you can take a look at this. Right. Election restriction. So this is a leader cannot be elected if it doesn't have the most up-to-date logs. Right. And committing entries from previous terms. So it has some information about that. I think these are the two parts. right? So the leader will commit log entries only when they have been replicated to majority of the nodes, right? This part is, I think, talking about this. And there is some other information also. However, a leader cannot immediately conclude that an entry from a previous term is committed once it is stored on the pre-majority of servers. So this information we have not covered in the class, so we can skip this for the sake of exam. But if you're interested, do give it a read. It has some extra information here. And the selection restrictions. So in my understanding, the selection restriction that a candidate cannot become the leader until and unless it has the most up-to-date log. So that is the most important part of safety. Okay. So this section completes the raft algorithm by adding a restriction on which servers may be elected leader. So this is the most important part of safety.
Sir, how do we compare logs to check which has most up-to-date logs?
The log index and the term associated with the index.
Okay, so I was asking in terms of like number of committed entries and non-committed entries.
So what's your question?
So let's say, do we first match like the number of committed entries in the leader should be more?
Yes, definitely. So first we check the term, right? So you see this receiver implementation for request vote RPC. If the term is lesser, if the candidate's term is lesser than the node's current term, then you have to deny the vote, right?
Oh, okay, sir.
Right? And then you check the candidate's log. Candidate's log is at least as up to date as the receiver's log. So by up to date means that you check the last entry basically.
Okay, sir.
What are the number of entries and then what is the term for the last entry? Both should match.
Sir, last committed entry, right?
Yeah, so let's go to section 5.2 and 5.4 to double check. So this precisely explains. So it's 5.4, right? Yeah. Raft determines which of the two logs is more up to date by comparing the index and term of the last entries in the logs. Right? If the logs have last entries with different terms, then the log with the later term is more up to date. If the logs end with the same term, then whichever log is longer is more up to date. So it doesn't talk about committed and uncommitted.
So, but won't this be problematic because in case of network partition, the smaller partition nodes might have the larger term.
I mean, smaller partitions will not be able to make any progress because there won't be any leader.
Yeah, but no, but when the partition heals.
Right, when the partition heals.
Yeah, so then they would have to wait for the term to get bigger, right?
No. So when the partition heals, the smaller partition, there the term is higher.
Yeah.
Right, and then the current leader is having a lower term. Right. So let's see what happens when when a leader sends an append entries message to a follower or to a node which is having a higher term. Right, what happens in that case? Essentially, that will resolve the situation, right?
So it just updates its terms number and steps down from the leadership.
Yeah,
And
that is
then
what
you,
I mentioned. So
yeah.
I already mentioned that, but I'm just confirming again. So I already mentioned so we discussed this scenario when we were discussing our network partitioning, that if a leader with a lower term sends an append entries RPC to a node with a higher term, its append entries RPC will be rejected and it will revert back to a follower. I mean, it will revert back. It will give up its leadership and wait for a new leader to get elected.
Yeah, so I get that, but here it says that they only the terms of of the two nodes are going to be compared. So the nodes that were in the network
No. So
partition
here,
in the
so are
smaller.
you referring to this paragraph here? Raft
Yeah,
determines which of the two logs is more up to date.
yeah.
No. So here, so this comes into play only when you're deciding whether you want to vote for the candidate or you don't want to wait for the candidate. It has nothing to do with append RPCs, append entries RPC.
Yeah, okay, but so for example, the network partition is healed, and
Right.
the 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 node that was in the smaller subgroup has a term of, for example, 10, and the rest of the nodes have a term of, for example, 5,
Right.
right? Yeah, so when one of the smaller when the one of these nodes that have a term of 10, they contest a leader election, they would
Right.
win when they should not, right?
I see. So what you are saying is, no, so they will not win, right? So come back here. So actually, let me just draw this. So they will not win. Let me just draw this to clarify. How will I share screen? So let's redraw this, specifically taking the scenario which Mitakshi is saying. So we have 7 nodes, 3 nodes in this partition, 4 nodes in this partition. Initially, this is the leader, t equal to 1. Everyone is just t equal to 1. Network partition happens. These nodes make progress because this leader is still functioning. These nodes try to contest election. Because of this, they keep on incrementing their term. So let's say at some point they have incremented to t equal to 10. Okay, now the network partition heals. In this case, there are two things happening. One is the leader is going to send request RPC, append entries RPC. Append entries RPC, right, to all the nodes, right? So the answer which I gave previously was that this append entries RPC will be rejected by these nodes because they are having a higher term, right? So we'll double check from the paper itself, but for now let's assume that this is right, that this will be rejected, and this leader will now turn back to a follower, or it will give up its leadership basically. So this much is clear, Mitakshi?
Yes, sir, and it will update its term also.
It will update its term. So this term gets updated to t equal to 10, right? Now let's also keep a track of which entries are where. So let's say this log file, the length is, let's say, 10. Here the length is, let's say, 2. Okay. So now what do you want? So should we, let's say this node is conducting the election.
Yeah.
Right. So what will happen? It will send the request vote RPC. So no. So it will send the request vote RPC to all, right? Now for the sake of simplicity, assume that each of these lengths are 10. So each of these nodes have length equal to 10. Or if 10 is confusing with t equal to 10, let's keep it as 20. Okay. Now if so this node is contesting the election, it is going to send request vote RPC to all. All of these are going to reject the request vote RPC. So all these 4, this one, and so this will be rejected. This will be rejected, this will be rejected, this will be rejected. Why? Because their log entries, they are having higher number of log entries than this, its own.
So, but doesn't the paper say that the term is compared first, and if the term is equal, then log entries are compared?
Yes. So in this case, the term is already equal, right?
No, the term is greater for the other node.
Right. So in this case, so this node has updated its term, right?
Yeah.
So they will so this a rejection will be received for the request vote surely on by this node,
Okay.
right? So the only contest is that only question remaining is what about these nodes? They have not updated their term, right? So let's see what happens. So let's go back to the paper. So let me try to open the paper here on the iPad itself. Just a second. Okay. So let's go to the safety section. So let's just quickly read this 5.4.1. In any leader-based consensus algorithm, the leader must eventually store all of the committed log entries. In some consensus algorithm, a leader can be elected. So let's just ignore this. Raft, so let's read from here. Raft uses a simpler approach where it guarantees that all the committed entries from previous terms are present on each new leader from the moment of its election, without the need to transfer those entries to the leader. This means that log entries only flow in one direction from leaders to followers, and leaders never overwrite existing entries in their logs. Raft uses the voting process to prevent a candidate from winning an election unless its log contains all committed entries. A candidate must contact a majority of the cluster in order to be elected, which means that every committed entry must be present in at least one of those servers. If the candidate's log is at least as up to date as any other log in that majority, then it will hold all the committed entries. The request vote RPC implements this restriction. The RPC includes information about the candidate's log, and the voter denies its vote if its own log is more up to date than that of the candidate. RAF determines which of the two logs is more up to date, and that so this paragraph is just about how do you check which of the two logs is up to date. So Mitakshi, the answer is, first of all, the term has to be compared. After the term has been compared, then you will check the logs also. If the term itself is lesser, then anyway you won't get the vote. But if the term is equal or higher, then you have to check the logs. Is
Okay,
this?
sir. Got
Does
it.
this make sense?
Yeah.
Okay.
Yes, sir.
So
Thank you.
okay.
Sir,
Any
can the
other question?
term number be overwritten during the request for RPC?
I think there is one possibility. So let's go back where this. So so the question is, if can a candidate update its term number during the
Candidate or follower even.
So let's take a concrete example. So let's say there is an election going on, right? So should we take some example? So here, see, let's first read this paragraph. While waiting for, so let me actually import this into good notes. So let's read this. So what this paragraph is saying here. While waiting for votes, a candidate may receive and append entries RPC from another server claiming to be the leader. If the leader's term, including in its RPC, is at least as large as the candidate's current term, then the candidate recognizes the leader as legitimate and returns to follower state. If the term in the RPC is smaller than the candidate's current term, then the candidate rejects the RPC and continues in its candidate state. Right. So this is actually talking about append entries RPC. It is not talking about request vote RPC. Right. So your question is. So let's actually now take a look at your question. So your question is. So can you repeat your question, Sonu?
Can the node update its own term number during the request vote RPC in follower or in candidate state?
So let's take both scenarios, right? So one scenario here we can see is, let's say these. So I think it can update. So I'm just still thinking. So let's take a simpler scenario. Let's say if it is a candidate, right? And so candidate will, so that the way terms are being used, right? So let's actually go back to the paper. They actually talk about how these terms, I mean, what are these uses? What is the use of this term? So let's read this, right? So different servers may observe the transitions between terms at different times, and in some situations, a server may not observe an election or even entire terms. Terms act as a logical clock in Raft, and they allow servers to detect obsolete information such as tail leaders. Each server stores a current term number, which increases monotonically over time. Current terms are exchanged whenever servers communicate. If one server's current term is smaller than the others, then it updates its current term to the larger value. If a candidate or leader discovers that its term is out of date, it immediately reverts to follower state. So, and if a server receives a request with a stale term number, it rejects the request. Right? So this is talking in general. It is not talking about a specific request vote or append entries RPC. So I think, yeah, so till now, whatever we have discussed, all of that remains valid based on this discussion here. So here, what it is saying is, whenever the servers are communicating with each other, so it could be request vote RPC and or append entries RPC. Whenever the server identifies that its term is smaller than the other, it updates its current term to the larger value, right? Because the purpose of terms is actually for the servers to identify that they have obsolete information, right? So my understanding based on this paragraph and the overall understanding of Raft is that it doesn't harm the candidate or follower to update their terms if they see a higher term floating around in the cluster. So anyone who has a different opinion, viewpoint. Shaunak?
No, sir, makes sense.
Yeah. So any other questions on Raft? No questions? All right. So then should we close the discussion on Raft? I mean, we can come back to it if required, but it would be great if you can ask your questions now on Raft. Okay, all right. So then we'll close the discussion on Raft. So we have discussed two-phase commit and Raft. So then what else is remaining? So anything else you want to cover in specific?
Sir, I had a very quick, short question in HDFS.
Yeah, sure.
Sir, in that you've mentioned that CRC32 is being used for correctness, to check correctness of data, and every 512 bytes, the CRC hash is calculated, and in that you mentioned that the overhead, the bytes length of CRC hash is 8, but I've checked on the net and the standards, and it's actually 4 bytes. So I just wanted to confirm.
Honey, so numbers might be wrong. So
Okay.
I mean, just understand the concept. So see, so
Alright.
there is some this. So what is it called? You basically ensuring that the data which is being received is not corrupt.
Right.
You do that using basically you do this checksum, right? So now how exactly you compute the checksum and all, so that might vary. So that's not so important.
Okay. All right. Thank you, sir.
Yeah.
Sir, I also had some question in HDFS. So in one of the lecture slide, it was mentioned that there is no demand paging for metadata.
So let me open the lecture slides. So I think what it was said is the entire metadata is stored in memory, right?
Okay.
So demand paging, as far as I recall from operating systems, is you don't keep the entire data in memory. Whenever the page is requested, you bring it on demand from the disk.
So it basically means that since the entire data is in memory, so you don't bring it to the main memory and just directly access from the memory.
The memory is main memory, right? What other memory you have?
I mean, you basically don't bring it to. You basically directly accesses from the main memory only.
See, demand. So I may be wrong, but demand paging is useful when you can't basically it is not possible for you to hold the entire data in memory, or you want to support holding data. Even if you can support all the pages, even if you can hold all the pages in the memory, you don't want to do it so as to make space for other processes, right?
Yes.
So in this case, in MapReduce, they are keeping all of the data in memory only. They're not keeping any of the pages outside the memory, so as to ensure that the metadata retrieval is fast. So basically the principle is the metadata retrieval should be fast. For this to be fast, always you have to ensure that all of the data is in memory and you are not fetching any of this data from disk.
Okay.
Make sense?
Yes, sir. Sir, there was one more thing. It was written in slide only that cluster is active while rebalancing.
Cluster is active while rebalancing. Yeah.
So I didn't understand how could cluster be active. So if you are moving data from one node to another, do we not need to like pause the cluster so writes don't conflict with moving the
So see, whenever the write is conflicting, at that point you will put a lock and you will ensure that they don't conflict. But it's not necessary that all the writes are going to conflict with the move, right?
Oh, okay. So if a write is
Depends on what you are moving.
then
Depends on what
pause
you are moving.
that particular node.
Yeah, obviously. Yeah.
Okay. And one more thing, it was written in slide only that the HDF is not for low latency. I didn't understand this point, like how it is not for low latency.
So it's not for low latency. So if I recall, I think in the slides it is written that it is for high throughput and not for low latency. Is that what it is written?
Yeah, high throughput and not low latency. So I didn't get it exactly. Like, मतलब, what does it mean कि low latency पे काम नहीं करेगा?
So first of all, what you need to understand is that throughput and latency are two different things. So throughput means how many requests you are going able to process per second.
Okay.
Okay. Latency is how much time is taken by each request.
Okay.
So what SDFS is providing you is it is providing you scalable. It is a scalable file storage system. It is scalable in the sense that the throughput can be very high. You're not doing anything specific to lower down the latency.
Okay. So it may take
It may take a
long.
large duration of time to read a block. So you're not doing anything specific to improve that. All you are doing is you are trying to parallelize your reads or writes so that the throughput can be increased.
Okay. And when we say that HDF is scalable, we basically means it in terms of read writes.
Yes.
Yeah. Because writes take even more time uh, if we were not doing the replication.
Correct.
Oh, okay.
So not just in terms of replication, right? You can write different blocks parallelly.
But in the slides, was not it that we write to data node 1, then data node 1 write to data node 2, then data node 2 write to data node 3?
Oh, I
Like
see. So you're
data
referring to the pipelining. No. What I'm trying to say is that so what did you just say? Like few
I
minutes back
was
you were saying something,
I
right?
was
What is your understanding of?
I was just saying that by replication, writes take more time because we need to write more data.
Right.
But reads are faster in this case because. Oh, okay.
So reads are faster, writes are obviously going to be a bit slower because you have to ensure data is replicated. Any other questions? So distributed snapshots will cover. So someone was asking about distributed snapshots. Antonio, were you the one?
Sir, before we go to Chandy Ramport, there was one example in map reduce that reverse web link graph. So I didn't understand what we were trying to do in that example.
Reverse web link graph, it's basically, let's say you have a web page and then
Okay.
that web page is, I may be wrong, I'm just trying to recall what it was doing. So it's basically what it was doing is if a web page has links to 10 different web pages, so then reverse web link graph is what it is doing is those 10 different web pages will have this source page in its list. So what this means is given a link, so given a set of web pages you want to, and the connections between them, you want to store an index to identify which link is available, is being accessed on what pages. So there
Okay.
is a source page and then there are targets. So for every target you want to construct the list of all the sources.
Oh, okay, sir.
It's similar to inverted index basically. So is that what the slide is doing? Because I don't remember what the example was doing. I'm just saying
I
based on
was
my.
not clear on what the slide was doing in the example, so that was why I asked the question.
So let me open the slide just to confirm. Mostly it is doing that only. It is similar to inverted index, but let me just check. So in the lecture, I didn't cover reverse. link. I think maybe you are referring to the
I think it should
other
be
set
in
of slides.
I think it is in lecture 14.
Lecture 14. Okay, let me check.
14 or 15.
So that is what it is doing. So you have, is my screen visible?
It's showing the raft paper.
Now also?
Your screen is not visible, sir. Not right now. Okay, now it is visible.
So here, that is what it is doing. So you have a set of HTML files, right? And then, so each file is a source, right? And then each source has multiple targets or multiple links within it. So for each link within the source, you are identifying. So that is called a target. So the map function is essentially outputting this target comma source, and then you're collecting all of these sources for this target. So there are 10 web pages. Each web page is referring to some other web pages within its content. So you basically pick up whatever links each web page is referring to, and for each of these links, you construct this reverse web link graph. So essentially what we were doing in inverted index, right? For each word, we were identifying which documents it is in. So similarly, in reverse web link graph, for each link contained in the documents, we are identifying from which document it is coming. So here the document is a HTML file or a link. That is what it is saying.
Okay, sir.
If you did, so did you understand or any other
Yes,
confusion?
yes, sir.
Okay.
Sir, one more thing. In lecture 16, you discussed an example on how to calculate the availability of a system.
So those questions will not be coming in the exam.
Okay.
Anything else?
Sir, could you discuss candy lampposts if there is time
Yeah,
for
I'll
that?
discuss that. I'll discuss that. So I'm just taking some
Yeah,
questions in the interim. I'll discuss.
sure.
Anything else apart from Chandy Lamport's distributed snapshot algorithm? So I think STFS MapReduce, you've already looked at the study material and you also did your project. So hopefully the concept should be clear, including the practice problems which you've discussed. So that should be sufficient. For Raft, we discussed almost all of it just now for the last 1.5 hours. For two-phase commit, we already discussed the entire concept again at the beginning of this meeting. Chandy Lamports we'll discuss now, and I think BitTorrent and blockchain are relatively simple, but if you want me to discuss some of the concepts from them, I can definitely discuss. So apart from distributed snapshots, anything else you want to discuss? Okay. So give me 15 minutes. I'll take my lunch and then we'll start again. Okay? Okay. So we'll keep the meeting online. You can remain online if you want. We'll start again in 15 minutes. So we'll start at 3:30 again. All right.
Yeah, thank you, sir.
Okay. All right, so let us get started again. I hope you are able to hear me.
Yes, sorry, sir.
Okay, so just give me a minute. Okay, so let us get started. I'm just trying to let me open the slide. Just give me a minute. I'm opening the slides. So Antonio, you wanted to discuss distributed snapshots, right? And yes, you also wanted to discuss, right?
Yes, sir.
Okay, so I'm just trying to ensure if everyone is here who wanted to discuss. All right. So let me add an introductory, add a page here to explain, just give an overview, a background of this snapshot algorithm, why is this required and all that. And then we'll directly jump into the algorithm. Okay, so what we are discussing is, so okay, so let me add a page here. Distributed snapshots. So first of all, why is this required? So notice that for so in case of fault in the system, right? So for fault tolerance, we have raft, right? And so two-phase commit is also part of fault tolerance in some sense, right? Or let's just ignore this for now. We already discussed raft and 2PC. So distributed snapshots, the entire purpose of distributed snapshots is while the system is active or is making progress in terms of accepting client requests, processing client request, and so on. we want to take a snapshot of the system's state without any interference in the system's progress. System's progress. So the system should continue to work. So the system should continue to be available to the end user, to the clients. And while the system is available, we want to take a snapshot of the entire system state. And why do we need this snapshot? So that in case of failures, if we want to, or failures or crashes or whatnot, we may want to restart the system from a previous point in time. So more graphically, let's say this is the timeline, right? And then your system is performing, let's say, operation 1 here, operation 2 here, operation 3 here, operation 4 here, and so on, right? Operation 10, operation 11, operation 12. Right? And so notice that this is just a single timeline, although this is a very simplistic timeline. In reality, we have a distributed system. So the system is distributed. So we have multiple components, right? And so here we are just saying the time, some notion of time wherein we are representing the entire system's time, right? So what we want to say is that, let's say a failure happens at this point. Let's say a failure happens at this point. So what do? Do we, so it is possible that when a system has failed, it was performing some action, it was performing some operation. So we can't just restart the system as is, because it is possible that there might be some inconsistency in the system. So what we do is we take checkpoints, we take snapshots or checkpoints. So this can also be called as checkpointing, checkpoints or checkpointing. So we take snapshots or checkpoints at regular intervals in time. So for example, let's say we can say this is our first checkpoint. How do I represent this? Let me represent this using a different color. Let's say this is checkpoint 1, C1, right? This is checkpoint 2, let's say. So if a system fails here, what we do is we are sure that so we'll have these checkpoints, checkpointed state. So what we'll do is we'll restart the system from this point in time. So we'll redo operation 11, we'll redo operation 12, and so on. Okay, so what I'm trying to motivate is, why do we need snapshots, or why do we need checkpoints? Why do we want to checkpoint the system's state? So let me try to explain this using one more example. So you all must have used, I'm guessing you must have used TensorFlow or PyTorch, right? So I mean, I've not personally worked with PyTorch, I worked with TensorFlow. So TensorFlow has this checkpointing mechanism, right? So what it allows is, so let's say you are training a model, and that model takes 5 hours to train. And if you are checkpointing every hour, so what will happen is, let's say a model fails after 4.5 hours. So what you can do is you can restart the training from the 4th checkpoint, which will have the trained model up to 4 hours of time. So you only have to do 1 more hour, right? and apart from that, you're already done, right? So, so this checkpointing is used at a lot of places, and since machine learning is common, very, very common these days, you might have come across checkpointing in TensorFlow also. Okay, so now the challenge, what we are focusing on is, you might be running the model on your own machine, right? So that is very straightforward. Whenever you want to check, whenever you want to take a checkpoint, you can just store the state of the laptop, the memory or storage disk or whatever, and then just make a copy of it at some other location, and then you can keep making progress towards the end goal. But in a distributed system, you have different machines. So how do you take snapshot in a distributed setting where you have multiple machines? So how do you coordinate between these machines to come to a consistent state? So how do you take a snapshot, or what kind of snapshot do you? So how do you ensure that whatever snapshot you are taking of each machine, each node in the system, and each network link in the system, how do you ensure that your the state which you have checkpointed, which the snapshot which you have collected, that is in consistent state? So this is where this distributed snapshots or Chandy-Lamport's algorithm for distributed snapshots comes into picture. So I'll straight away jump into the lecture, jump into the algorithm. The algorithm is very simple. So what does the algorithm do? So algorithm is very simple. What it does is, so consider a distributed state system. So first of all, how do we characterize a distributed system, or what are the components in the distributed system? Number one is the nodes which are participating, which are part of this distributed system. Second is the channels or the network links which are connecting these nodes. So the Chandy-Lamport's snapshot algorithm, this is snapshot algorithm, it stores the state of each node and of each channel also. So let's say you have this distributed system and they are connected to each other via these 5 channels. Only these 5 channels are there, let's say. So Chandy-Lamport snapshot algorithm will, so when you say I have collected a snapshot of this system using this Chandy-Lamport's algorithm, so I will have state of each of these nodes and each of these links. So 4 nodes, 5 channels. Right? And these are unidirectional channels. For example, we could have more channels also. For example, we could have 1 channel this way and so on. So in this case, we will have 6 channels. Right? So now the algorithm, what it tells is, when do we start, how do we start the snapshot, or whenever we start the snapshot, what information do we need to store, and when do we end the snapshot. So in this algorithm, there is any one process. So it talks about in terms of processes. I just drew this diagram in terms of nodes. So you can call these nodes also as processes. So more generally, these are processes. So these processes could be running on the same machine. They could be running on different machines. So let's actually rectify this. So when we are not referring to nodes, we are referring to processes. So distributed system essentially means a set of processes and channels. Which channels are basically the bridge which are used for communicating between various processes. So in the snapshot algorithm, so I'll cover the algorithm. Algorithm is very simple. Then we'll take 2 examples, and hopefully it will become completely clear. So in the snapshot algorithm, there is an initiator process. So any process can start the snapshot, can start the checkpointing. So once the process starts, what it will do is it will it will save its own state, right? So own state, it's nothing but a piece of, state basically refers to some data or whatever data you want to store as part of the state of the process. So that will vary from process to process. For example, in TensorFlow, the state would be the trained model parameters which you want to store, latest model parameters which you want to store as part of the state. So once you have saved your own state, Okay. Once a process has saved its own state, it will also send a marker token along all the outgoing channels. So for example, in this case, what will happen is, let's say if we start from here, if this is the first process taking the snapshot, it will store its own state, and then it will send the marker token along all the outgoing channels. So these are outgoing channels. So what will happen is, it will send a marker token along this outgoing channel. This is just to signify, just to inform the other process, this process that I have, it is so this marker from process 1 is to signify, is to inform process 2 that I have already taken the snapshot of my state. Now you go forward and take the snapshot of your state along with some messages which I might have sent along this channel. So what are the other processes going to do? Whoever receives this marker, so in this case, this process 2 is going to receive the marker. What it will do is, whenever it receives the marker, it will first save its own state, right, and propagate markers along outgoing channels. So then it will further send the markers along all the outgoing channels to which it is connected to. For example, 2 will now send to these two channels. So this is, let's say, 3, this is 4. Right, in this case, the algorithm proceeds, and whenever all the processes have saved their state, the algorithm stops. Right. So there is one piece of information here which is not given here. So I'm just trying to look. So whenever this receiving process stores, so whenever process 2 is going to save its state, what will also happen is, it is possible that before this markers channel, there was some message M1 which was sent. Right. So this process 2, the receiving process, will also keep the state of this channel, store the state of this channel. So remember that we are defining this distributed system as a set of processes and channels. So we want to store the state of each process and each channel also. Now channel is unidirectional in the sense that it has one-way traffic from sender to receiver. So the state of every channel is stored by the receiving process. So for this channel, the state of this channel is stored by process 2. For example, for this channel, the state is saved by process 3. Right. So in the end, what we want is, so I'll take an example to explain this more. In the end, when we say use the distributed snapshots algorithm or Chandler-Lampert's algorithm to construct the snapshot, to build the snapshot for this distributed system. So in the end, what we want is, we want the state of each process and the state of each channel. What all information is stored in the snapshot for each channel. So in the process, we'll have state of P1, state of P2, state of P3, state of P4, and in the channel, we'll have the state of channel from 1 to 2. State of channel from, so I'm just trying to write down what all piece of information we need to store using the snapshot algorithm. State of 2 to 3, state of so this is also an outgoing channel actually, so it will also send a marker along this. So let's say it has already sent M2 here. So this is state of 1 to 3, state of 4 to 1, state of 2 to 4, one more is remaining, state of 3 to 2. So all these 6 channel state we need to store in addition to the state of each process. And who is going to store, for example, so for example, for this process, this channel C1 to 2, this channel here, the state will be saved by P2. For this channel 2 to 3, the state will be saved by P3. For this channel, state will be saved by P3 again. For this one, P4. For this one, P4 again. And for this one, P2. So each process, so for example, P2 will store its own state as well as state of this channel. Similarly for other processes and channels. Now how exactly
for 4 to for 421, won't it be channel 1? Oh, sorry, process 1 that would be storing it.
You're right. So for process 421, this would be P1. Yeah. Okay.
Yes, sir.
So now let's take an example to further understand how it works, or what do we mean by state, right? So I already gave some idea, like think of you're running any process, it is doing some computations and it is running for 5 hours. Then you want to resume, let's say you don't want to waste whatever you have computed for, let's say, so let's say the entire duration of process running the process is 5 hours, but your process fails at 4.5 hours. So you don't want to waste the computation which you have done for the last 4.5 hours. So what you do is you do regular checkpoints. You do a checkpoint at t equal 1 hour, 2 hour, 3 hour, 4 hour. So if it fails at 4.5 hours, you can start your processing from 4 hours. Whatever state was there at 4 hours. So you only have to redo the half an hour work. You don't have to redo the entire 4.5 hours work. Okay, so now let's go to the tutorial or the example, right? So you can read through this entire blog post. I am just skipping the introduction. I already explained most of it. So let me actually export this. So I already have this, I think, in my drive. Okay, so what is happening here? So let me just read this just to ensure that you have understood the basic. We are going to model the system we are snapshotting as a collection of processes that can send and receive messages among themselves. And sending and receiving are events that take place on processes. In this example also, there have also happen to be internal events that are neither sends or receives. So there could be 3 types of events. One is these internal events. Second is sending events, and then receiving events. So think about the logical clocks which we have discussed in the past. Messages are sent and received along channels which are FIFO queues going between each pair of processes. It turns out to be important that the channels are FIFO behavior for the Chandy-Lamport algorithm to work. So we'll say that processes in our system are named P1, P2 up to Pn, and the channels from process Pi to process Pj is named as Cij, essentially what I was referring to. For instance, the channel from P1 to P2 is C12, while the channel from P2 to P1 is C21. A snapshot is a recording of the state of each process, that is what events have happened on it, and each channel. So when we say give me a snapshot, I should give the state of each process and each channel, and within each process I should tell what events have happened, and within each channel I should send what messages have passed through it which have not been seen by the some of the processes, which may not be seen by some of the processes. So Chandy-Lamport algorithm ensures that when all these pieces are stitched together, so when we assemble all these pieces together from different processes and channels, they make sense. That means they are consistent. So in particular, it ensures that for any event that's recorded somewhere in the snapshot, any event that happened before that event in the distributed execution are also recorded in the snapshot. This is an important statement. We'll come back to this later once we have gone through the example, then it will become more clear. What it is trying to say is that if we are capturing an event in the snapshot, then all the events which have happened before, or all the events which are causally dependent on this event, all the events on which it is causally dependent, those are also part of the snapshot. So this is essentially referring to the causal dependence. Causal. Okay, so let's see. So here is an example. there are three processes, each with several events, including messages sent and received. Dots on process lines with incoming or outgoing arrows are internal events. So here what is happening? We have three processes, P1, P2, P3. And what is going to happen is, so these are very similar to the logical clock questions or the vector clock questions which you have done in the past. So we have different processes and each process has some events which are happening. Some of them are internal events. For example, this A is an internal event. And B is the sending of a message. F is the receiving of that message. And so on, right? For example, J is this internal event. Okay, and then what is the goal of this snapshot algorithm? What is the state which is, when we take a snapshot of this algorithm, what is the state which is what is the state of P1, P2, P3 and each of these channels. So here the assumption is that P1 is connected to P2 through a channel, P2 is connected to P1 through a channel, P2 is connected to P3 through a channel, and P3 is connected to P2 as a channel. P1 is connected to P3 as a channel, and P2 is also connected to P3 is also connected to P1 with a channel. So there are 6 channels in total. So you want to store the state of all the 6 channels along with these 3 processes. Okay. So let's read what this says. One cool thing about this algorithm is that it is decentralized. Any process could start the snapshot without coordinating with other processes. Right, and even if multiple processes start simultaneously, it doesn't create a problem, as we will see when we go through the example. So let's say, so here it says, let's suppose that P1 initiates the snapshot right after event B has happened. So when P1 initiates the snapshot, what it will do? Let's go to the algorithm, right? So what is the algorithm? The algorithm is initiator saves its local state. So what is the local state? Let me move this. Right. What is the local state of P1? So P1 state is, let me write this down here. P1 state is, if it starts the snapshot at this point, that means A and B have already happened. So P1 state, we will depict P1 state or we will denote P1 state by A and B. So those are part of the P1 state, which is the part of the snapshot. Now what will happen? Let's take a look at the algorithm. So algorithm says, send marker tokens along all the outgoing channels. So what are the outgoing channels? One outgoing channel is this P1 to P3, right? Another outgoing channel is P1 to P2. So we need to send markers along these 2 channels. So let's see what it does. So now let's take a look at this. So P1 has taken the snapshot of its state. So its snapshot is represented by this A and B circle which includes both A and B. At this point, it has sent a marker. So these markers are represented by these arrow signals. Now these markers are received on P3 at this point and P2 at very late, right? So now let's see what the algorithm says. So initiator is done basically, right? Other thing which initiator has to do is, which is not written in the algorithm, it will start recording the state of C21 and C31. So recall that P1 has sent the marker along the outgoing channels. But what about the incoming channels? So for the incoming channels, what are the incoming channels? C21 and C31. It will start recording if it now sees any messages on these channels. So now think like, why do we even need to store this information? Because P1 has already taken a snapshot of its state. So now if P1 receives some message from P2 or P3, it will not be part of this state, right? So then we have to keep it as part of this state, C21, the channel state. And using this, we can reproduce the entire system state later on when we want to restart at some point. So is this clear what P1 is doing? P1 is doing 3 things basically. One is it takes snapshot of its own state, right? So P1 says, I have stored my own state, which is A, B. Second, it sends the markers to P3 and it sends the markers to P3 and P2, right? which are denoted by these arrows, the dotted arrow line, send markers along C13 and C12. Thirdly, start recording C21 and C31. So these are the three things which process P1 is doing. Now let's see what we should do. So now what we should do, we can start maybe taking a look at some of one of these two processes, P2 and P3, right? So for the sake of simplicity, what we can do is we can just see what happens at P3. So P3 has not started taking the snapshot yet, right? So at this point, it will receive a marker from P1. So as soon as it receives a marker, what it should do? It should basically save the state and propagate markers along outgoing channels. So the explanation is not incomplete here. So P3 will also do these three things. So P3, what it will do? P3. So P3, what it will do is it will store its own state. So P3 state would be this thing, this thing here, the event I, which has happened before the marker was received, right? So it would be I. Additionally, what it will also do is it will also finalize the state of this channel. Finalize the state of the channel on which it received the marker. So what is this channel? This channel is 1.3. So it will finalize the state of 1.3 as empty because it has not seen any other message apart from the marker. So marker is not part of the snapshot state. Just notice that and note that marker is not part of the snapshot, the final snapshot. It is just an indicator, as the name suggests. It is just a marker to say that some processes started snapshotting, started checkpointing, and so on. So it has finalized the state of, recorded the state of C13 as empty, meaning that there are no pending messages on C13 which are to be processed by P3 because P3 has already added I in its state. Third thing which P3 is going to do is it is going to send markers along the outgoing channels on which it is the sender, right? So it will basically send along C32 and C31. And fourth thing is what it will do, it will start recording the other incoming channels to which it is connected to. So C13 is already finalized. So what is remaining? C23. So it will start recording C23. Right. So let's see what the example says. So that's what it is. Some explanation is there. You can take a look at this explanation at your own time. So essentially receiving what does the process do when receiving a marker? It does four things. And these four things are exactly the same four things which I listed here. So here what P3 has done, see, it has recorded the state of C13 as empty, and it has started recording the state of C23 on which it is the receiving process, and it has also sent a marker on the other outgoing channels. So what are the outgoing channels? P32, P31. So these blue lines, these depict other set of markers which are sent by P3. Right. So now let's see what happens at what do you want to process. So let's see, this point comes before this, right? So we can just process this what happens on P1. So on P1, remember P1, what P1 was doing? P1 was recording the state of C21 and C31. Now it has received a marker on C31. So therefore it will close the state of C31. It will finalize the state of C31 and store it as empty. Right. What else it will do? It has already snapshotted it. It has already taken the snapshot of its own state. So it will not again take the snapshot of its own state because it has already taken the snapshot. But the problem here is that the C event will not be part of the snapshot, but that's fine. Right. So we'll take a look at if this impacts our snapshot state or not. But as of now, the C event will not be part of the snapshot of P1 because P1 has already taken the snapshot, its own snapshot as A and B. So this is already done. So therefore this C will not be part of the snapshot. And what else it will do? It will close the state of C31. It will still keep listening to C21. It has already sent markers to other outgoing channels. So therefore it won't do anything else. So remember that any process sends the markers only once. And when does it send? Only when at the first time when it receives the marker or when it starts the snapshot. Okay. So let's see what happens. So see, notice that C31 has been finalized. Its state has been recorded as empty. It is still listening for C21, and C1 process P3 is also listening for C23. So we are sort of done with P1 and P3. Now let's take a look at P2. So P2 will first receive the marker from P3, right? So what will happen? So here what will happen is P3 will first take its own snapshot, right? So what it will do, it will construct this entire thing. Okay. So P2 state will have F, G and H, because it is receiving the first marker after F, G and H have happened. What else it will do? It will record the state of this channel.
Sir, I had a doubt. How are we making sure, like, how are we deciding where the marker is going to?
So we are not deciding. It is sort of assumed here. So in terms of, so it will be given to you basically. So
Right. So
yeah.
in the question, it would be given to us that okay, the marker.
Right. Okay. So P2 will finalize its own state. It will also finalize the state of this channel from P3 to P2. So this would be, so have we received any message here? No, right? So this would be empty. Okay, so let's see. Right. Now what else it will do? It will then send the markers to both P1 and P2 because it has not sent any markers.
Sir, why is C3 to empty? Hasn't it received a message from I to J? So I to G. So shouldn't that be stored?
So that is already taken into consideration in the P2 state, right? F, G, and H.
Right. So if we were sending some message, let's say M through I to G, so that is stored in P2 only, and it is not considered in the channel, right?
So those messages which are already received, which are already taken into consideration in the process state, we don't double count any message basically.
Right. Okay.
Okay. So let's see. So C02 is marked as empty and sends out its own markers to P1 and P2. So P1 and P3. So now P2 is going to send markers. So P2 sends markers, marker this and marker this marker and that marker. So what will happen? Right. So let's just quickly close down P2 first. So what P2 will do? When P2 receives this marker, it has already taken its own snapshot. So it will just close down this channel P12 as empty. So C12 will also be empty. Right, and that's all. It has already sent its own marker, so it will not do anything else. And it has already closed the other channels. Right. So now let's go to P1. P1, what it will do? P1, when P1 receives this marker here at this point, so what will happen? So now this is an interesting case, right? So what has happened here is, recall that P1, when it took its snapshot, it was recording C21, right? C31 it has already finalized. So before it actually received the marker here, it has received this D message, right? So C21 will have D in its state, and then the state of C21 will be finalized and recorded. So this is an important point here. Make sure you understand this. P2 sent a message H, and so sending of the message is represented by H, receiving of this message is represented by D. After the D, the marker is received from P2. So before the marker, there is an event which has happened of receiving the message, which has not been taken into account in the state of P1. Therefore, this channel state, channel from C21 should store this message D, so that in the final state, we should be able to say P2 has sent a message H, sent a message, and that event is taken into account in the P2 state. But P1 already took the snapshot before, so therefore it did not take into account this D. So this D is taken care of in the channel state. I guess now you should be able to see why we want to store the state of the channel.
So what will happen with C in P1?
Yes, so C will remain as is. C will not be part of the state of P1 still, since this is an so C will not be part of the state of P1. Neither it will be part of the state of C21, because C has nothing to do with C21 first of all, because this is a channel. So C is an internal event. So C is an internal event, and therefore it won't be part of any state.
Okay.
So sir, then why wasn't process C, the event C was not recorded in C31?
Come again?
Why wasn't event C not recorded in C31?
Why? Come again.
As in, why wasn't event C in P1 not recorded in channel 31?
3.1.
Yes.
3.1. What is 3.1? So 3.1 is the channel from 3 to 1, right?
Yes.
So this is an internal event, right? So what is P1 doing? P1 is keeping track of this channel C31. So C has nothing to do with channel C31. So channel C31 is this channel. So along this channel, what all information is flowing? So C is an internal event. It has nothing to do with the information flow from P3 to P1. So before this marker, there is no other message which is being sent on this channel. So therefore, C31 is empty.
Okay.
In the other case, P1 to P2, first of all, this message, which can be referred to as H to D, was sent, then this marker was sent. So therefore, we need to store this as part of the C21 state. So let's rewrite this. So we should write it as message, or whatever way we want to say, message from H to D. Okay.
Yes, got it.
So let's see what happens.
So what if the marker arrived after E?
That's fine. That is not so event E has nothing to do with this channel of C21. So the channel of C21 will still have D only. So even if this arrives here, it has nothing to do with this event, because this is some other event on some other channel.
So like I don't get it. Like why? So what will happen with E then? So is it getting stored anywhere, or we will completely lose the E to K?
Depends on when this. So E will be lost because P1 has already sent its marker on P13, which was received at this point.
Right.
So any messages on this channel P1 to P3 will be ignored after the marker is received. So this might be a little bit confusing. So let us actually finish this finish this example, check the contents of the state which we are recording, and then it will make sense, right? Then when you actually look at the result, then hopefully it will make sense, and then we'll discuss what is included, what is not included, why it is included, why it is not included, does it make sense to include something, or does it not make sense to include something. So all those questions we'll discuss. Okay. So C21 we so where it is. So see, P1 still has to finish up, though it's waiting for a marker to come in from P2, so it can stop recording on the channel C21. Hey, look, that marker message just came in. Did any messages get recorded on C21? Yes. The message whose send event was H and whose receive event was D did. So that event goes into the C21's final channel state. So notice this. C21, the message is represented as H to D. So that is part of the channel. Now only thing remaining is this marker here, right? When this marker is received, there is no other event which has happened in between. So P3 was listening on the C23. There was no other message being sent from P2 to P3. Therefore, C23 is also empty. Right. So this is the final state. So let's take a look at this. P1 is storing A and B. P2 is storing FGH. P3 is storing I. Along with that, all the channels are empty except the C21, which stores S2D. Right. Now let's take questions. So for example, why is the C not included? So actually, let's understand how this snapshot will be used. Right. So how this snapshot will be used? Let's say there is a failure now. Right. Now we want to restart from a previously taken snapshot. So in that case, what will happen is we will apply so that whatever state we revert to, that state will have A and B applied already, FGH already applied, I already applied, right? Now you think, since A and B are already applied, that means the receive of B should also be in the system states. F is already there, right? Similarly, you see I to G, both are there in the system. Then you see S to D. If you don't add this D, then we will be having an inconsistent state wherein we say that P2 had already sent a message, but it was not received by P1. So we need to store this information about D somewhere. So that is stored in this channel, right? And what about C? Now what happens to C? Since what will happen is, so think about like how these operations are getting executed. So you will have a piece of code somewhere. So whenever you revert and then you restart, C is an internal event. So you can still again reproduce it. So whatever piece of code you will run, you will again reproduce C. So C will get reproduced. And then based on the timestamp associated with S2D, right? You will also be able to order these C and D accordingly. And then E, of course, is independent. Similarly, K and J, these are ignored because these are not part of these. J is internal event. This will anyway be reproduced whenever we restart, and K is going to be there because E is going to be re-executed whenever we restart. So yes, so you had some questions, right?
No, I think I get it. So one question I had was, what if the marker reached after K, but now since E is not getting stored, so that marker won't store K as well, right?
So other way to think about this is, which this blog post also explains, it is sort of storing this information. So what is that? So anyway, this so this read just this paragraph. So it says that for any event recorded somewhere in the snapshot, any events that happened before that event in the distributed execution should also be recorded in the snapshot. So that is all this snapshot algorithm is ensuring. So any event you pick up and you check all the events that happened before this event, that should be part of the snapshot. So for example, let's say you pick up H. So what are the causally so what are the events on which what are the events on which H is causally dependent? Event G, event I, event F, event B, event A. All of them are in the snapshot state, right? Similarly, you consider if you don't consider D, right? So if you consider D, so for D, what are the causally dependent events? H, G, F, A, B, I. All of them are there in the state, right? So any event you pick up, it's causally dependent events. They will be part of the snapshot. Okay. So any events that happened before that event in the distributed execution should also be recorded in the snapshot.
Sir, I have some doubt regarding the markers.
Right.
How we are deciding the order that the process will receive the marker from other process. For example, in P1, when it will first send markers. It will send markers to P3, and P3
Right.
is receiving the marker first. Then P2 is receiving the marker too late.
So this
What
is
is happening?
this would be given in the question. So this information will be given in the question, or
Okay.
so in the example it is already assumed that this is how these markers are being received.
Okay.
So we are not deciding; it is part of the example.
Okay, I got it. Thank you.
Hello.
Hi.
Hi, sir. Sir, like my question is not on this topic, but I just wanted to ask, like in the two-phase commit, you have shared the video by Martin, and like in the last part, there is a algorithm for like getting fault tolerance in two-phase commit. So I just wanted to know, like, would that algorithm be a part of the syllabus?
No. So actually, I didn't take a look at the entire video myself. So I think some of the details in that lecture might be extra. So you should just limit yourself to whatever we have discussed in the class or in the lecture slides. So just make sure
Yeah,
that
because
if it is there in the
yeah, that
lecture slides,
algorithm
yeah,
was not there. Yes, sir.
yeah. So then you can
Uh,
ignore it.
Also, like for the lecture on fault tolerance, availability, reliability, like would we be getting some questions similar to the kind we had in cloud computing, like the graph
No.
comes and we. Okay, sir.
No.
Thank you. Answer another question. Like, sorry,
Yeah.
but like in the document that you have shared for the practice questions, in the section uh, of HDFS and the question number 3, like the question says that we are given a HDFS cluster with a name node and approximately 150 bytes of memory is stored per uh, data item.
Entry.
Yeah. So basically, like, let's suppose, matlab, I just wanted to ask, like, why are we not taking the replication factor into consideration? So,
Let me just check.
yes, sir.
So just a second. Let me share my screen again.
Yes, sir. Third question of HDFS. Yes, sir. Sir, it says that each file like requires approximately 150 bytes. So let's suppose there are 100 files. So like, why
No,
don't we
this is
consider it
the
as 100?
this is no,
Yes, sir.
this is the this. So here if we are talking about name node. So name node
Yes,
doesn't
sir.
have replication. So whatever information is there, it is
Yes, sir.
only stored in one. There's only one copy of whatever information is there in the name node.
But like, let's suppose there was a file that we want to store. Okay, so we store like the metadata of that file in the name node. But when we replicate that file, we will again have some metadata, and we would want to
No.
store it in
So
the name
here
node.
metadata means that all of the information related to replication, how many blocks are there, on which data nodes are there, they are stored and all that. All that is part of the metadata.
Okay. Got it. Thank you, sir.
Okay. So any other questions on distributed snapshot or any other topic?
Yes, sir. I have some question in lecture 21, slide 17.
Yes, please tell.
Okay, Mike, like I didn't understand, like this is about snapshot algorithm.
Right.
It's regarding single token system, the scenario when there is no token in the system.
So just ignore the single token and all that. Just try to understand the simple snapshot algorithm which we have discussed.
Okay.
All that is just additional detail which is not required.
Okay.
For the sake of the exam.
Okay.
Any other questions? So I actually have to stop early. I mean, I want to stop early because I have to prepare the exam. Also, I'm halfway through. Half of the exam is still needs to be prepared, and then I need to take the printouts also. So yeah, please tell if you have any questions.
Sir, we have a couple of doubts if you don't mind us asking.
हाँ हाँ बताइए.
Uh, एक बार हम स्क्रीन शेयर कर लेते हैं.
Sure.
Right, we start with Hadoop. So either you had mentioned something about batch processing, so we did not understand this last point.
Yeah, so Ananya, I'll share the recording of this session. So it is going to be a 5-hour recording. So it will take, I think, at least 1 hour on the Google Cloud server to get processed. So I think I'll share it somewhere in at around 8 or 9 p.m. Okay, so
Right.
yeah, Diksha, you were telling something?
Yeah, so
Huh.
what ये batch processing का you had mentioned, we didn't quite understand this point.
So essentially what it is saying is, so there are two types of data analytics. So when we talk about data analytics generally, so there are many dimensions across which we can categorize data analytics. One dimension is batch processing versus stream processing. So MapReduce specifically meant for batch processing, meaning that so when you start the MapReduce job, you sort of assume that your input data is going to be static. So there are going to be no more changes in the input data, right? So you have fixed your input data. So once you start the job, any changes in the input data will not be part of the analytics or whatever processing the MapReduce is going to do. So that is what is meant by batch. So essentially what this means is, let's say you have, so some example can be, let's say you want to run a MapReduce job every 5 hours. So whatever changes happen to the data in the last, whatever changes happen to the data, when you start the system, when you start the job, after that, and if any changes happen to in the data, they will not be part of the data processing. They will not be part of the data processing. Compare it with stream processing. In stream processing, what happens is you keep on processing the new data as soon as it arrives into the system. But here, this is not what it is. What is happening here? What is happening is you're sort of assuming that your data is static, and no changes are going to happen to the data. If some changes do happen, then you have to rerun your entire job to incorporate those changes in the data.
Got it. Okay, sir. So next out.
So this MapReduce is meant for batch processing. It is not meant for stream processing.
Okay, sir. Next we had a doubt, like you said that secondary name node is not a compulsory component, like it does
Right.
not reside in. So like if the name nodes like get destroyed or something happens, is down or something, like so how data nodes know, or like how can we create it back or something?
So let's say there is no secondary name node and the name node fails. So what information is the name node storing? Name node is essentially storing what all files are there. For each file, what are the file blocks, and where all these blocks are stored. That's all, right?
Right.
So what you can do is so how the name node will reconstruct this entire metadata image? It will reconstruct by traversing all the data nodes.
Okay.
Going to all the data nodes, asking the data node what all file blocks it has, and then it will use that information to reconstruct this metadata. So for example, here you take a look at this path here, right? Some username and then data and then part 0, part 1 and so on.
Right.
So using the file path also, it can identify which file it is and how many parts are there and where all they are stored. So it is basically going to traverse through the entire disks of each and every disk of data node, and using that, it is going to reconstruct itself. So it is possible to reconstruct it from scratch.
Okay, so like no one will know that the name node has crashed or something, like because the heartbeats are going in one direction only. Like data nodes only send the heartbeats to name node, but name node does not send the heartbeat to data node.
Right. So
So
if the data, so ultimately, it will have to be done manually. So it is not an automatic process here. So it
okay.
has to be done manually, basically. Yeah.
And FS image is a compulsory component, right?
So FS image is essentially, uh, basically, it is sort of storing the state of the entire STFS, what all operations have happened and all that. Yeah. So that is a compulsory thing. It's basically a checkpoint. So the thing which we were discussing just now, right? Snapshot. It is just a snapshot of the entire STFS system cluster.
Okay, so if we want to know the basic difference between FS image and the secondary name node, is that FS image is the snapshot and the secondary name node is just the replica of a name node.
Yes, yes. So FS image might not have all the operations which the name node has performed.
Okay, but secondary
Because
name node will have.
secondary name node will have, because as soon as an operation gets executed on name node, it is also replicated to secondary name node.
Okay. So here we had doubt about this low latency and high throughput thing.
So here all what we are trying to say is that MapReduce. So first of all, let us understand the difference between throughput and latency. So latency means how much time it takes to process a write request.
Okay.
Throughput is how many write requests can we process so how many write requests can we process per second.
Okay.
So request per second, that is throughput. Request taken for a time taken for a single request, that is latency. So STFS provides high throughput because it is parallel, right? You can process multiple writes in parallel because there is sharding and so on. But the latency is not ensured to be low because each write operation can take a relatively long time also.
Okay. So it takes long time because of that, uh,
So one
sending
of
the
the reasons is
acknowledgement.
acknowledgement and then replication and so on.
Okay. And so what does we mean by cluster configuration management here?
Cluster configuration management essentially means like if you want to add more data nodes, for example, and all that,
Okay, so
or
basically,
remove.
okay, so everything is done by the name node. Okay. Also, I had a doubt. So here we have written that we can delete the files, but in the starting it was written like we can only append. So append at the end of the file. So we can't update the files by by changing the data that has already been written above, but we can only append and delete them.
Yes.
Okay. And what does this paging means? Like,
Paging is basically you have to go back to your operating systems course.
okay.
So for a process, you can have multiple pages of memory. So a process can be allocated multiple pages in the memory. Now let's say your main memory size is 4 GB, right? Nowadays, let's say it is 16 GB, and a process requires let's say 12 GB of memory, right? So you can actually accommodate the entire process in all these set of pages. You can keep all the pages which are required by the process in memory, right? But that leads to only 4 GB remaining for other processes,
Right.
right? So what happens is, so I might be 2% wrong, but from what I recall in operating system, that is what we studied, that it is possible that you only keep some of the pages which are required by the process right now, and other pages you can bring on demand from the disk or the what is that? There's some other term which is also used, right? Swap space,
Okay, so
right? And so demand paging here, what it means is that for MapReduce, we don't do demand paging. We keep all of the pages in memory all the time. Entire metadata is in main memory always. There is no demand paging.
okay, sir.
Right. One of the major doubts that we had was you had actually given a link for a video. In the video, they had mentioned that if you're writing blocks on a particular data node, like let's say two blocks A and B, that's done parallelly, but writing on the data nodes is sequential. But here you have written that one block is written at one time and then we move to the next block.
So actually, I didn't take a look at the video completely. I just skimmed through the video and saw that it had some related contents. So but still, let me try to understand the question and answer it. So here what we are saying, client retrieves a list of data nodes on which to place replicas of a block. So that is for write. Client writes block to the first data node. The first data node forwards the data to the next node in the pipeline. When all replicas are written, client moves on to write the next block in file. So here what it is saying is that the client is writing the files, the contents of the file one by one in order sequentially, right?
Right. It's written here like first we write block 1 and then we write block 2. But in the video it said that block 1 and block 2 are processed parallelly basically.
Okay, so let's okay, so we can verify this from the paper. Let me open the paper.
Okay.
Just a second.
Should I stop sharing?
No, you can keep it. So see, I'll share my screen also, and I don't think you can write multiple blocks of a file in parallel. I might be wrong also, but let me share my screen. So two things. One is, let's first read this part here. This is what exactly the slide was saying, my slide. When an application reads a file, the SDF, so are you able to see my?
Right,
Yes,
sir.
sir.
When an application reads a file, the HDFS client first asks the name node for the list of data nodes that host replicas of the blocks of the file. And it then contacts a data node directly and requests the transfer of the desired block. When a client writes, it first asks the name node to choose data nodes to host replicas. The client organizes a pipeline from node to node and sends the data. When the first block is filled, the client requests new data nodes to be chosen to host replicas of the next block. A new pipeline is organized and the client sends the further bytes of the file. So each choice of data nodes is likely to be different. So this is basically saying that it is doing sequentially, right?
Right. Then
One
we
after
do
the
nothing wrong.
other. So then the other part is also there. HDFS client that opens a file for writing is granted a lease for the file. No other client can write to the file. The writing client periodically renews the lease by sending a heartbeat to the name node. When the file is closed, the lease is revoked. Right. So basically, it is basically saying the same thing now. The
No.
data nodes form a pipeline, and
So like
yeah. So you were saying something.
if the same client has to write two blocks, then it will write sequentially. If two clients have to write, then also they'll write sequentially.
Right.
Yes, that is what the paper is saying. It's not explicitly saying, but that is what it seems from the explanation.
Okay, sir.
Okay.
I'm sharing my screen again for the doubts.
Okay.
Yeah, we're done for Hadoop, but we had a couple of doubts in BitTorrent as well.
Yeah, so can
Okay.
I? Yeah. So one of the doubt is what does this hard to control means as a motivation and issue?
See, hard to control, the motivation is that it's not in control of one entity or one leader or one government, right? So let's say if you want to share some information with the common mass, then there is no way you can stop it on BitTorrent. That is a positive. It's a negative also because sometimes you don't want to share the information to the general masses, but still it gets spread through this BitTorrent type of system.
Okay.
So that is an issue also.
Okay. Then we had the doubt in the protocols.
Okay.
So like here what does this seed and leeches mean? First of all, like there were
The
two
seed is
doubts.
basically so seeds are seeds are those nodes that have some portions of the file and they are sharing that file, uploading that file content to the leeches. So leeches are the downloaders, seeds are the uploaders basically.
Okay. Okay. And then this like what does this slide mean? Like
This is just the start of the algorithm. So let's say there is only first peer. So seed is essentially the first peer with the complete file. So let's say in the beginning, so let's say now you decide to share a file using BitTorrent. So you only have that file right now. So only you have that file right now.
okay.
So you are the seed, right? So other peers who want this file have to contact you.
Okay.
To get the portions of the file. So that is what it is saying. So first step is you get the torrent link. So seed is the one. So if you take a look at this 1, 2, and 3 point here, right? So first step is get torrent in this figure only.
Acha, this figure only.
Get torrent metadata. Right. So you have to download some torrent file from somewhere. So what that torrent file contains? That torrent file is essentially a link to a server which will tell you for this particular file what all nodes have some of the pieces of this file. So that is the tracker. So tracker is the one which is keeping track of which portion of the file is present on which node, which peer.
Okay.
So using this torrent file, you go to step 2, you get the list of peers from which you can download. And then you start downloading trade chunks with peers. So trading chunks means you download something from them and then you upload something to them.
Okay. So
try to relate this to the BitTorrent application which you might have used, right?
Right.
So you download a torrent file, click on it, it opens this BitTorrent software and then it starts downloading, right? So when you click on the torrent file, you're essentially contacting the server, the central server which has this information about where this file is stored, what all peers this file is stored on. So you basically what you do is you divide your file in let's say 100 pieces. So you download 5 pieces from peer 1, 5 pieces from peer 2 and so on. So you can download multiple pieces of the file in parallel.
Okay. And so choking and unchoking here.
So choking and unchoking is very simple, very simple. So if you're downloading something from a peer, you should also do upload to that peer. So it's tit for tat, right? So if you are taking something from someone, you should give something in return. If you're not giving something in return, then you will be choked. So your download speed will be slower than. So let's say you are only downloading, you're not uploading anything. So your download speed will become slow.
Okay. Essentially, if we do not have anything to offer, let's say at that particular point, and we need to download rather, so wouldn't we be choked in that
We will
scenario?
be choked. We will be choked. We will be choked in that scenario also. So our download speed will be slower.
All right.
And like this was the main slide we had is showing. So
So this you can ignore because anyway we didn't cover DST in the class. But what this slide is saying is, I just mentioned the tracker is a central entity. But let's say you don't want the tracker also to be a central entity. So tracker is nothing but it is keeping an index, right? For which file, what are the peers? So
Right.
mapping from file to peers. for each file an array of peers, right? That is all what the tracker is storing. So
Right.
instead of having a single server which is storing this entire index, you can distribute this index over multiple servers, and that is achieved using this distributed hash tables.
So everyone knows what all is stored where.
Not everyone. Someone know, some peers know some portion of the index. So it's basically, let's say your index has 10,000 entries and you have 10 peers. So it is possible that two peers have first 2,000, next two peers have next 2,000, and so on.
So like, but every peer knows now, like these all indexes are stored with this peer.
No. So the DST are a bit more involved. So DST, you don't replicate the entire information. You only replicate a some portion of the information. So basically your question is, does every peer know the entire index? Answer is no. Does every peer know what all where all some portion of index is stored? Answer is no. So it's basically it's not straightforward.
So if a peer wants to download something from other peers, so how will they contact if they don't know what all is stored on that peer?
So they will basically they might have to make multiple hops. So let's say they will go to peer 2, then peer 2 will say, I don't have it, then they will go to peer 4, something like that.
Okay. Also, sir, that lecture on fault tolerance is not in the syllabus, right?
Not in the syllabus.
Okay. So we just have just a small doubt for MapReduce. Like, do we mention the number of mappers or reducers in start, or like, are they inbuilt?
It varies basically. It varies. You can decide. You can also tell the MapReduce job how many mappers to have, how many reducers to have, and maybe the MapReduce. And if you don't tell, then the MapReduce job also can figure out. Will try to figure out on its own.
So, like, let's say we have 5 partitions, so it is not necessary that we have 5 reducers. Like, number of reducers can vary from the number of partitions.
Definitely, mappers and reducers need not be the same.
I think that's it. Thank you, sir.
Thank you, sir.
Okay. So any other questions? So I'm planning to finish by 5 p.m.
Yes, sir. Sir, I had one doubt. Yeah, sir, in the last slide of lecture 20, it is written that for a common case, there are 3 end messages: prepare, then the response for prepare, and when the coordinator sends the abort and commit. But like, I just like, wouldn't there be a 4th message where the like nodes reply for the abort commit?
Fourth इसलिए नहीं, so fourth is not there because from the perspective of the client,
yes, sir.
The client, the transaction coordinator sends back the response to the client immediately after the third message is shared with the participants.
Okay.
So as soon as the as soon as the transaction coordinator decides that it has to commit or abort,
yes, sir,
it sends back the response, commit or abort, to the client.
Okay.
Right.
Yes, sir.
The fourth is also not there, but in practice, yes, that would also be an additional cost.
Okay, sir. Got it. Thank you.
Okay. Any other questions?
Yeah, sir, blockchain पे कुछ questions हैं नहीं वैसे आपने लिखे नहीं है.
Sorry, what?
Sir, like, you have not shared any questions on blockchain.
Yeah, I have not prepared any questions on blockchain. So blockchain, you see, we'll have very simple questions of whatever, some simple theoretical conceptual questions from what we have discussed in the class.
Okay, sir. Thank you.
Okay.
Yes, sir.
Sir, very minor doubt from the blockchain slides. So there was this that we will be choosing the longest chain, right? But then in the last slide, in the Nakamoto consensus, we decided that we'll be selecting the chain with the highest 2 to the power difficulty summation. So is this not contradictory? Like, or am I getting it wrong?
It's not. So it's not strictly longest, it is longest in terms of the work which is performed.
Okay. Oh.
So longest is not just it. So we are interpreting longest as in terms of the number of blocks.
Length, yes.
Length. So it is not in terms of the length. In proof of work, yeah. So in proof of work, it is in terms of the amount of work which has been performed.
Okay. Great. Thank you.
Okay. Siddharth, you have any questions? Okay, so then we'll close for today. If there are any more questions, just ping me on Google Chat or email, whatever works, WhatsApp. All right.
Yes, sir. Thank you.
Okay, all right. Thank you.